Okay, thank you. Okay, very good morning to all of you. It's a pleasure to invite you all for the inaugural of third greenhouse gas workshop and conducted this year at IITM. So the official title of the workshop is National Training Workshop on Greenhouse Gases, Observations and Inverse Modeling on Indian Regional Perspective. So today we have our director IITM to give a welcome to the audience and welcome to the workshop. Sir, over to you.
Thank you. Thank you, Vinu. Good morning, all the esteemed delegates and Professor Dadwal, Dr. Prabir Patra, my good friend from Jamstack, Dr. Vinu, Dr. Supriyo Chakravarti, Dr. Yogesh Tiwari, and all the participants from various parts of the world, actually. Although it's a national workshop where several institutions from India are participating, it's also good to see many faculty from different parts of the world, from Japan, from UK, from US, and various other places. And so I am happy to welcome you all to this very important workshop on the workshop on greenhouse gases, observations and inverse modeling on the from an Indian regional perspective. This is a very with climate change becoming such a important event that we are seeing this everywhere, extreme events and floods, and so it is a reality now. And also the 2021 Nobel Prize in Physics went to the groundbreaking contributions of Professor Suki Manabe. Almost more than 50 years back, he had highlighted the importance of how carbon dioxide and greenhouse gases can affect the global climate, and all the statistics of the extreme weather events, the hydrological cycle, monsoons, heavy precipitation events, floods, and so on. So it's become a reality. Now the carbon dioxide in the atmosphere is something like 414 or 415 parts per million, a significant rise compared to the pre-industrial concentration. And this is happening almost at a rate of 2.2 parts per million per year. And so this has been a steady increase, and largely due to the effect of human activities, due to the fossil fuel combustion and so on. And in addition to carbon dioxide, also methane has been increasing in the atmosphere very significantly. And so we have another 15 years of carbon budget left for the 1.5-degree warming, and which is definitely from the AR6 projections, we know that 1.5-degree warming global mean temperature increase compared to the pre-industrial time is expected in the next 15-20 years. And so the way the fossil fuel consumption is happening, it's happening at a very alarming rate. And unless very serious and sustained mitigations are done, very rapid and also sustained mitigation in the GHG reductions are done, so limiting warming to 1.5 degrees is going to be almost impossible. And 2 degree, we can still do our best to limit our warming global mean temperature by end of the 21st century. By following sustainable approaches, we may be able to limit to 2 degrees. And I'm sure Dr. Prabir he's also a lead author in the IPCC-AR6 in the chapter 5, and they have done a very, very rigorous assessment. And I'm sure he will present some of these findings. And so both carbon dioxide, also methane is increasing, but regionally there are a lot of variations in the fluxes, both from the natural sources and also from the anthropogenic sources. So there has been understanding based on the satellite data and the in situ data. We have a much improved understanding of these regional variations in the GHG fluxes in different ecosystems. And IITM is also having a program, is leading a program of the Ministry of Earth Sciences to understand the GHG flux variations in the different ecosystems. And Professor Dadwal, who is an expert in this and was pioneered this from India, from ISRO, and he has made, and ISRO has also got a network of these observations. So we need both these observations to understand the regional variations as well as models. Without models, we will not be able to understand this problem. And I'm very happy to see this. There is both, this workshop is focusing on observations as well as inverse modeling over the Indian region. And I'm sure this is, and I have seen the agenda and also the program, which looks very, very impressive. The kind of speakers, the experts from different areas, and there is also hands-on training. And I'm sure this is going to be a very, very productive and useful workshop. So I welcome all of you, and thank you all for joining from various parts of the world to this very important and very necessary workshop. Is highly relevant. And so I thank IITM, especially the DESK program, for taking up this initiative. And once again, I wholeheartedly welcome all of you, and let us make this program very successful. Thank you, one and all. Jai Hind. Jai Bharat.
Okay, Jai Hind. Thank you, Dr. Krishnan, for a wonderful welcome and putting the workshop in place in its background, linking climate change and greenhouse gas cycle. So now I invite our scientific steering committee chair, Dr. Prabir Patra from Jamstack. He doesn't need an introduction at all. All the people present here are well aware of his works, extensive works in greenhouse gas modeling, inverse modeling, and is a very renowned personality in the global greenhouse gas cycle in the world. So it is very honored to have you here. Dr. Prabir, please share a few words about this workshop.
Yes, Vinu, thank you very much. And yes, Dr. Krishnan's wonderful beginning for us. He laid out the foundation of this workshop very well. So thank you very much, sir, and also allowing us to host this workshop again in IITM. This has been very nice things to happen. So again, welcome to the National Training Workshop on Greenhouse Gases, GHG-3. So observations and inverse modeling on Indian regional perspective. I am actually very honored and privileged to be part of this since its inception. And I cannot thank enough to the local organizing committee and the scientific steering committee how much time and effort they have put, and also asking me to stay involved in this activity. So let me start by congratulating both the committees for putting this impressive workshop program, also echoed by our director IITM. So I'm sure we'll enjoy every bit of it on the next 4 days. And I just wanted to say a few things here, although I have 10 minutes, but I'll not use all of them. And since we started this workshop series, we can see that the greenhouse gas research has diversified. In just these 3, 4, 5 years, we see a lot of changes, the way we do research, the way our research is used in the media, for example, in the government and discussion, and all the things have changed. And one of the things probably the changes happened in the Paris Agreement in 2015, where there's a kind of a image shift in the people's mind that in Kyoto Protocol it was like a mostly voluntary basis. So some of the countries were asked to reduce, which are like a kind of Annex 1 country that defined, which are kind of rich and who have been emitting greenhouse gas over the long time. But then in the Paris Agreement, these things changed in a perspective to that, and every country can commit their emission mitigation targets. So it's still voluntary, but it's still like you have to tell before what you're going to do. So this is what the COP26, even this year, was a lot of discussion. I think most people followed in the news and media, and also happens every year. This COP happens every year, and then dialogues, negotiations, and how the NDCs are requested. Actually, NDC, although things still sounds like that it's completely voluntary, but I think there is a pressure on us to act. And as also echoed by Krishnan before, is that also this year 6 has put these things in the perspective that we need to act now. And so that also our research has improved in many different ways. So the amount of observations we have today, So amount of the observation, the biomass, the satellite imageries, the vegetation information, the crop cycle, fires, the ground-based satellite-based observations, it's increased in huge amount. And it happened from like GoSat was launched in 2009, and then OCO2 came up in 2014 end. So all these things like adding to the millions of observations and billions of observations. So now we really need to have the models, high quality models, to use these high quality observations, and then we can actually improve our understanding at various scales. Like we have to understand in the district scale maybe, and then go to the state level, and then the national level, and then the regional levels, because this greenhouse gases is building in such a way that we cannot limit our understanding to one particular scale. So imagine that your ultimate goal is to have a global CO2 concentration to be reducing in future. And this has to happen from every human being's activity. So that the scale is huge. So from individual activities, the way you live in your house, the way you drive to your office, so all these things are counted up to the global carbon budget, and that is the one number in the globally. And so everything has to come together to be able to track how it is changing and who is changing and where it is changing and how by how much, all these things. So I think, and with this kind of also ideas, like you might have heard that UNFCCC, the United Nations framework on the climate change, and so they're actually thinking about having something called global stock take. So every country basically produce an assessment of their greenhouse gas budget or the nationally determined contributions, and then everything will be globally stacked up, and then we have a global budget, and then you see how it is changing with time, and the policy we implement today and how it is affecting your concentration change. It is maybe CO2, it may be methane, it may be N2O, it may be HCFC. There are many greenhouse gases, even including ozone, which is a reactive species, but it also is a big greenhouse, very effective greenhouse gas, although its lifetime is very short. But these things has to go down from the air pollution point of view, from the greenhouse gas point of view, and then we have a much healthier Earth. And so see, these things will happen in global stock take. That's a kind of a policy, the top level policy, but then this has to be fed up with the scientific understanding at every level, so that each government can act to effectively reduce greenhouse gas, for example. So then I think I also want to mention two events that has happened recently. That one is that mentioned by Krishnan, IPCC, that Dr. Krishnan was like a coordinating lead authors, which is like a top level authors in this report. So every chapter has 2 or 3 of them, and as a lead author, we are like 10 or 12 to 20 of them in each chapter. So their assessment is very solid, and I would also like to say that this assessment also largely depends on the kind of observations which is of the past, and also the model simulation, which is kind of a CMIP6. We call it CMIP6 climate model integration project or something. It's a level 6. It's a match to the AR cycle. So it's AR6, CMIP6, and these results, like when you completed the report in January this year, 2021. This working group report was just finishing, and that is just before that the CMIP6 models are all getting submissions, like even submission at the level of time of the writing or finishing the report. So that means you can imagine how much information is just being gathered by the CMIP6 database. I think the participants should also be, please take note of this kind of things. What is going on locally in your university or institute or the state, and what is also happening internationally. So you can take advantage of this huge amount of database, huge amount of facilities and information people are producing for you to ingest in your system, in your analysis system. And of course, you all know that we are working in the midst of pandemic, which is like just the COVID-19, and it's maybe happens living less than once in a century. So we are like so much uncertainties. So our lives have lots of hardship for many different ways. Everybody is facing some sort of hardship. So some people lost their even loved ones. Global economy uncertain. But I think we need to continue these kind of activities, like this workshop, for example, to make an educated judgment on climate change and climate change mitigation policy. So as I said, it's like a country level, regional level, global scale, I think at all scale. And this is for our next generation. So of course we are going through hardship, but our next generation should not be put into more hardships, our children and grandchildren. So there will be no excuse that for us to hand over an unhealthy earth environment to them. For it's from global warming point of view, climate change point of view, also for the air pollution. We often talked about that. So and the greenhouse gas is basically heart of this problem. So our job, what we are going to do today, I mean, or this next 4 days is very, very important. And also one of the things I want to actually mention at the end is that this year workshop that we will see that we struggled in the first workshop to produce a lot of hands-on this one, but then this year's workshop is like many of the lecturers and the hands-on materials are prepared by the people who participated in the first and second workshops. I mean, nothing can be better yardstick than this to measuring success of this this series of workshop. I think this is a very, very healthy condition for us and very, very encouraging. And I really thank them all and keeping up with the pace. And then they learned a lot. They have some of them finished PhDs, some of them are working on them at the final moments. I think all the best wishes for you, the youngsters. And then thank you very much for actually helping us in this workshop. It's really, really nice. So I can actually enjoy the workshop this year very much. And also, as Professor Krishnan mentioned, that it's a big thank to the lecturers from the Europe, Japan, UK, and US for accepting our invitation. And you know that there like holiday seasons are coming. There, everybody is busy, but they still accepted to our invitation and they deliver lectures. Please enjoy, everyone. Thank you very much. I'll stop here. Thank you.
Okay, thank you, Prabir. Thank you for an excellent inaugural speech and bringing up the correct yardstick to measure how this workshop is beneficial for all these efforts. Okay, thank you very much. Now we have a chief guest here, Professor V.K. Dadwal. So it's my honor to introduce him to the audience, although he does not require any introduction at all. And he's a well-known scientist in carbon cycle from India. So he right now he's associated in Institute of Advanced Studies in AAC Bangalore, and he was director to IIST Trivandrum ISRO, and before that he was director NRSC National Remote Sensing Center ISRO, and held various other positions. And he is as Dr. Krishnan mentioned, is the pioneer to the carbon measurements, setting up various sites across India. So whenever we heard Sundarbans, it's like a monolova key term for India, Sundarbans observation. So he is the custodian behind the observational effort. And he has steered many scientific committees. It's endless. There are many to read out. So due to lack of time, I'm not reading out. And he has contributed for more than 300 papers in reviewed journal publications and edited books and many other. So, and he's also the opening batsman to this workshop. He's going to deliver the first plenary talk. So now I invite Professor V.K. Dadwal to share his few words about this workshop.
So good morning. Good morning, Dr. Krishnan, Dr. Prabir, Dr. Yogesh, Dr. Supriyo, and Vinu, and all the participants. So it gives me immense pleasure to join all of you in this third version of Greenhouse Gases National Workshop. In fact, in addition to these two workshops, there have been many significant meetings. We were just discussing with Dr. Prabir that we had one in the Chennai, in the Swaminathan Institute, I believe. Then we also, IITM hosted the Asia Flux meeting around 5 years ago. In addition, there have been various things like Asia Pacific remote sensing and other atmospheric science where carbon comes into picture. In fact, these days, it is very difficult to hold a conference and not have carbon or one of the climate change as part of the discussion. But what distinguishes this workshop is, as Dr. Krishnan and Dr. Prabir have pointed out, one is that we are trying to focus on India. Two, there has been a continuity and growth and learning by many of the speakers who joined previous workshops and have now been able to contribute and add to our understanding. Third, this will also become a part of the national assessment. Only I just would like to remind all the participants that India now has reached almost like between third and fourth position in the total quantum. But per capita, we remain below the global average per capita. Secondly, carbon is not what you emitted this year, today, or yesterday. In fact, it has been demonstrated multiple times. The temperature impact is linearly related to cumulative carbon emissions. So once it is cumulative, you need to really look at the cumulative emissions, while it is very easy to concentrate only on the current. This also brings in another challenge, which I will refer to. But before that, let me talk about the carbon cycle and some peculiarities of India. One, the India is basically South Asian subcontinent, and it dominates the carbon cycle of this area because maximum forest and population. Other people simply increment it, but the other part is on the positive side, India and China are the two countries where globally they have shown the maximum greening in the past decade or two and the additional carbon fixation. While we will concentrate on the human energy greenhouse gas emission and how does the natural vegetation or terrestrial ecosystems respond, there is very significant carbon cycle which happens in the hydrology section. And in fact, Himalayas are so prone for erosion, and the sediments which is carried by the Ganga, Meghna, Brahmaputra and also the Indus. In fact, in the Bay of Bengal, there is a great Bengal fan, which is basically in the ocean, which this carbon also gets deposited. And as been pointed out that the fire is a very, very big modifier. In fact, some of the recent papers have concentrated on quantifying the carbon, pyrogenic carbon, which comes because of the fire. After all of the coal which we are burning is also from vegetation, but this accelerated burning producing charcoal and getting distributed is also an estimate I think are required. Plus the way we have done irrigation, the way we have brought out the so many water bodies and dam, the hydrologic carbon cycle also has been significantly affected. In fact, the carbon cycle also strongly interacts with the nitrogen and phosphorus cycle. The reduced nitrogen totally changes the carbon cycling pattern. And in fact, in this regard, India and China, if you see, we have maximum irrigated area per hectare. We use large amount of nitrogen, but then we are all mostly dominantly vegetarian. So the carbon nitrogen interaction of a vegetarian dominated human society is quite different when you actually have the per capita meat consumption very high. So finally what happens, you end up with energy, water, carbon, food nexus. And this nexus is what the human society has to learn to manage this and evolve into the new patterns. But what I would still stress, we need to really also ensure that we have the participation and equal representation of all communities, because as of now, from the impact side, the most impacted will be those who are in the drier areas and island communities. So the impacts are likely to be not regularly distributed. So it is a global issue, and I wish all the participants well. I think the carbon cycle is more than your domain. It's truly a earth science issue. I'm sure you would use this opportunity to learn more and more about the various interactions between various submodels of the earth system and develop and contribute to understanding of this carbon cycle. Thank you very much, Dr. Krishnan, for giving me this opportunity and inviting me to join in the inaugural session of this very important workshop. Thank you.
Thank you, sir. Vinu, can I just
yes,
say
please
one?
Go ahead. Yeah.
Yeah, first of all, let me thank both Dr. Prabir Patra and Professor Dadwal. I think you have really set the stage. Thanks a lot, sir. And I'm very happy that you have brought out this point of a nexus between carbon and water cycle. In fact, there is a small cross-chapter box in the AR6 that has highlighted this issue, the nexus between carbon and water cycle. I remember I was also initially part of that team. So many issues we really don't understand, and this is a very, very important topic. Hopefully we can consider this in the subsequent workshops. And also the way these series of workshops, they're evolving, the participants and faculty, they're almost, they are appearing year after year in these workshops. I think it will be good to bring out a consolidated report at the end of 5 years to take stock of where we have and what is the real contribution that has emerged by this series of national workshops. Periodically, if you can do that, that will also be very important. Taking a documentation. This is just my suggestion. Vinu can think about it, and yeah. So thanks a lot, sir, for Professor Dadwalji and Dr. Patra. It's a great honor, and welcome to all of you once again. Thank you.
Yeah, thank you, Dr. Krishnan, for thanking the chief guest and the inaugural speech guest. So now we have a small portion to remain to introduce the background of the training workshop. So let me take that privilege and let me quickly go through it without spending much time on it. And I'm going to share my screen, and hope you all seeing the screen, and also you're seeing the full screen. So as we already discussed, this is a national training workshop on greenhouse gases, GHG-3, jointly organized by the desk program of the ministry and Indian Institute of Tropical Meteorology. So a short history of the greenhouse gas workshop evolved is in this manner. So GHG-1 conducted with the same steering committee. Dr. Prabir was also there as a chair in that session. And the title was National Training Workshop on Greenhouse Gas Measurements, Interpretation and Inverse Modeling, which sets the stage for this effort from in India, conducted in July 2017, and the first one conducted at IITM Pune. Then in the subsequent year, GHG-2, International Workshop on Land, Ocean, Atmosphere Interaction, Greenhouse Gases and Coastal Processes, LOA, conducted at ISER Kolkata in the July-August of 2018. That was the subsequent to the GHG, and then we call it GHG-2. But unfortunately, 2019 and 20, we faced the toughest time of perhaps in our life due to COVID. So we could not organize, and it went on a sleep mode. And then now we are rejuvenating it by calling GHG-3 and bringing back to its home National Training Workshop on GHG, Observation and Inverse Modeling on Indian Regional Perspective. So as we move on, we are giving more and more national importance to this workshop, and this is now held at IITM Pune. Now, the theme of this particular workshop, we have framed three key themes. This workshop is first intended to provide a venue to unify researchers from various scientific communities and share their information on the observational front of GHGs from India. So this is what we found a gap area. We need to unify various efforts going on in India in the observational front and see how we can go together. And the second is this workshop will serve as a venue to present and share the knowledge on the regional inversion aspects of India, which is also upcoming research area in India. in Indian greenhouse gas fluxes and methodologies adapted, etc. And third, most important, is the selected pool of students and early career researchers and scientists will be trained with a few hands-on in this particular aspect. So these are the three themes identified for this year workshop. So this is the program structure we are going to follow. We have 12 plenary talks of 45 minutes each, and there are 4 keynotes of 1 hour each. That's our schedule. And there are 4 training sessions of 2 hours each. So that's how we programmed in this year workshop. And we have a total 52 candidates as registered participants from MOES Institute, research centers, universities, etc. So they have been selected out of hundreds of applications we received. But to keep the focus of the workshop in place, as well as their experience and the benefit they may gain from this, we selected 52 excellent candidates to attend this workshop. So, and the first 2 days are dedicated for observational aspects, and the next 2 days are dedicated for the modeling perspective. And each day has 2 hours of panel discussion. So that's a special attraction of this workshop. We have kept a panel discussion in the afternoon hours, which is kind of closed door for delegates on respective themes of the day. So in these 4 days, they will brainstorm on it on the themes and find out a way forward as a recommendation from this workshop. That's how we are planning it in this year. And a large number of experts are invited to discuss on the identified problems and gap areas and challenges of the greenhouse gas researchers from the regional perspective. This will be discussed in the panel discussion each day. Now, organizing structure of the Greenhouse Gas 3 is that IITM Pune is the primary organizer, and the desk, which is the training unit of the Ministry of Earth Science, is coordinating it as one of its targeted training program. So that these two are the key coordinators to this workshop. And all meetings are via MS Teams in virtual mode, and meeting will be recorded for the training purpose, as well as a YouTube live stream link is already created. It's up and running for people, for wider audience who can attend to all the plenary and the keynote. So we are sharing it through the YouTube also. So once again, I thanks all of you for joining in this workshop. And I also use this opportunity to thank our director IITM for giving all the support throughout in this organizing this workshop and giving the venue and opportunity and bringing it back to home IITM. Also thank Scientific Steering Committee, Dr. Prabir is here, and all other members also who spend a lot of their time meeting and formulating this, and all the training coordinators, our young students and researchers, they are the wheels of these training programs they're coordinating. Thank you very much to all of them also. And I thank our chief guest to kindly honoring this occasion by accepting the invitation. And with these words, I conclude here, and I thanks all our organizers, our local organizing parties here, and they run up all the time for keeping this in time. So thank you very much, and I thank all of you once again for the participating in this inaugural session. So with these words, sir, we have come to the end of the inaugural session today, and now we will move on to the first talk, which is delivered by Professor Datwal himself. Yes,
excellent.
Sir.
Thank you so much.
Thank you. Yeah.
Thank you very much, everyone. So very nice.
Thank you very much, everyone.
Thank you.
All the best.
Thank you. Thank you. Professor Datwal, you may kindly load your PPT.
Okay. I have share screen. You are given.
Entire share screen would be good. Yeah.
Okay. Share screen from window.
Yeah. Can you go to full screen mode?
Yes.
Yes. Very good. So we can see your full screen mode. Okay, so good morning all again. So today's our first talk is by Professor V.K. Datwal on assessment and modeling of Indian carbon cycle results from National Carbon Project. Sir, you have 45 minutes, so we will give you some time intimation as soon as we reach the time. Thank you. So I'm very sorry. I have to invite Professor Dr. Supriyo Chakravarti to chair this session. So he's going to be the chair of the morning session today. Dr. Supriyo, are you there?
Yes, I'm here.
Yeah, over to you, Supriyo, please.
Yes. So I would request Dr. Datwal to deliver his plenary talk on assessment and modeling of Indian terrestrial carbon cycle results from National Carbon Project. Dr. Dadwal, please.
So thank you, Dr. Supriya. Good morning, all of you. We already, I think, discussed the preliminary background, and you are all aware of it. In this lecture, just wish to cover something which my colleagues worked for about more than a decade to really put up some estimates, numbers, and measurements over India at the pan-India scale. So, as you would recognize, you can measure something at one point, but to really have the full spatial heterogeneity capture, many measurements need to be done, especially for the terrestrial biomass, etc., for the entire study region, which is case is India. And there the remote sensing helps. So our interest was in this area, but then the biomass or the stock alone doesn't solve the cycle. The fluxes either have to be estimated. So I just would cover only the terrestrial biomass, soil carbon, and fluxes. The measurements of the gases, our colleague Dr. Mahesh, who is also part of the NCP, I think he is delivering separately. We will miss, I will not cover that. Okay. So I think we can skip the outline. This background is very well known to you, that there is increasing fossil carbon emission if over past 160 years. The fate in the last 10 years, as per the Global Carbon Project, 46% remained in the atmosphere, 31% got absorbed in the vegetation, and 23% in the ocean, and there is another 0.4% imbalance. So basically, when we see a emission total or additional, we still can't balance our carbon budget. So this better quantification, better modeling at various spatial and temporal scale, and to be able to explain this entire carbon balance is important. Because why it is important? Because some of the sinks can get saturated, and some, because of the response to climate, can change their direction or the capacity of the absorption. That exactly is the issue. Okay. So as far as the land part is concerned, we have net primary productivity. So the CO2 moves to the vegetation. Then there is a litter fall, and through root and the otherwise, the carbon moves to soil. Then through the heterotrophic respiration or conversion of land to other or fire, then there are emissions, right? This carbon cycle, which is the vegetation dominated, also has significant changes due to hydrologic carbon cycle, which is in the form of dissolved organic carbon, particulate organic carbon, and bicarbonate. The geochemical carbon cycle, the weathering, the human-dominated carbon flows of food, wood, fire, animal nutrition, plus the land use, land carbon and land cover change. So this makes it reasonably complicated, and you need to require all scientific inputs, whether it is Earth observation, whether it is ecological studies, whether it is the radioisotope, large amount of, plus the two additional things which have come. One relates to the eddy covariance flux measurement, so that the undisturbed ecosystem we can measure the carbon changes. Okay, so as part of the national carbon project, we looked at this issue, and this was a project funded by the Department of Space, ISRO, under ISRO Geosphere Biosphere program, started in 2007, originally for a decade. So what was exactly done was, one, flux towers were established for net carbon exchange. Also, atmospheric CO2 measurement as well as satellite retrieval was looked at. The land use change and deforestation and forest biomass map was also done. Soil carbon pool, ocean and coast we will not touch in today's lecture, but modeling of NPP was also using Earth observation data, a part of the NCP project. So what the government of India releases the Indian National Communication. So the NATCOM, the second NATCOM, and the biennial updates too are available. They use standard IPCC methodology, and they focus mostly on emissions, energy and other emissions. This do not truly capture the carbon uptake or the changes in the carbon density. Okay, so this is a part of the commitment which through MOEF and the various scientific organizations, including we also help and contribute in creating. The other part was the NCP looked complementary to it, but in one more sense. The forests which have the maximum carbon density are actually studied by FSI. So the Forest Survey of India does the plot measurement, but their sampling is such that they can estimate the carbon pools or the sizes at physiographic level, and now they also publish at district level. This is done through a sampling and a rotation. So the two cycles have different areas sampled. So the change, what you get, always has an issue. But we have looked at the forest carbon pool size from independent observations and independent data. Okay, so this is the another second difference between the what government statistics are available or the forest versus what the NCP project attempted. So what basically you do is you measure over a small plot the tree number, the girth and height, and then use a local volume equation to convert it into a volume and biomass. Biomass is then converted into carbon. But whereas the FSI used 1/5 of the district approach, so that in 10 years or 5 cycles, they can cover all the district. We followed a stratified sampling where the vegetation type, density, and the other biological or ecoclimatic zone was used as a parameter to lay out the sample. Second is the mean of the biomass or volume is not multiplied by the area, but the upscaling is via a remote sensing based model. Initially through visible NIR's model, then through microwave data, then use of the LiDAR and high resolution, and now machine learning based methods have been used. I'll show you the results and what it means in terms of the map of the biomass carbon. So a large number of institutions participated. So I thank all the PIs and participants who really did this measurements. So the measurements were made at 2,000, nearly 2,000 sites in cluster of 4 plots, so that 250 by 250 meter average number could be done. So this is the only biomass map or estimate which is totally independent of the government numbers or observations. So it has been generated from raw measurements by a very big, large team. Okay, so this we discussed. So basically, you take a 250-meter plot, you identify 4 plots of 0.1 hectare, measure all the trees, heights, species. Also in the subplots, you measure the herbs and shrubs. So what you can do now is to get an estimate of biomass, above ground biomass of the vegetation or the forest at various locations. Now, these are not averaged to compute the pool or create a map, but then we merge it with the various data such as the growing season, which is the vegetation index from remote sensing, various phenology, plus the climate, the topography, and then use it as part of the modeling by a random forest technique to really not only create a predicted map, but also an error estimate, right? So this, when in each zone you use a spectral model, you will see that you can create small such local models and create biomass maps. But such empirical model, a national one would really not be possible from the optical data alone. So these models allow us to move from, let us say, 0.1 plot to 5 by 5 kilometer average grid for local models. But for the pan-India national modeling, you require an entirely different approach. So this approach then, as we said, it used 6,000 plots, and the prior information available was that if you use the government statistics of the district-wise forest cover and then their carbon density, you would get a 1994 map, which basically we estimated around 3000 teragram, 2895 teragram, and its spatial distribution. But for the recent ones, where there were more measurements and distributed data, it is possible to add the new numbers and create for 2010, where the number comes to around 3176. So basically, it tries to suggest that in spite of some areas, you can really see in peninsular India that there has been a decrease. Also, the red, which is a very high carbon, so the red area which is now restricted in the Himalayas as well as in the Northeast, right? In spite of all such things, the total pool may have increased because there are more pixels even with the lower biomass. But the overall mean density is estimated from 677 to 80 tons per hectare. But then the forest cover also has increased by about 3 million hectare. That is, which is the FSI estimate of tree cover, right? So this gives an idea that yes, even when aggregated to an intermediate level, there are increase in the forest phytomass. So now we go to the enhancement of measuring high biomass, either using the very high resolution texture, which is discussed in this paper, or use the microwave data, because optical data gets saturated in contrast to microwave and LIDAR. So this is LIDAR data where the ISAT glass is used to really develop a model where the tree height is an additional parameter. So even for the same greenness, if you have taller trees, then they actually accumulate more carbon. So inclusion of tree height from the remote sensing enhances or improves the model prediction of the biomass. So this is then estimate where the L band as well as the LIDAR is used to create a biomass map for the country using random forest and tool. Now, we have now worked on enhancing or reducing the errors by still adding the microwave, the VIs, the phenology, the climate, the topography, the tree height to really this paper has been published this year where what we have been able to show a biomass map, the parameters which contribute uh, to or making this biomass in a machine learning model. But more importantly is that if you were to plot the biomass versus let us say backscatter, you will see somewhere around 140 to 160, the sensitivity decreases. If you use only optical data, it is sensitive only up to 100 tons. But when you use a machine learning model, where all these are plotted here. So now if you use the high volume observations, the observed versus predicted, and then you use 10% decrease in the slope as a parameter to estimate saturation. What we are able to demonstrate that a machine learning approach which merges LIDAR, microwave, optical data, phenology, and bioclimate does not saturate up to 330 tons per hectare. So it means we are able to really map high biomass points because these high biomass points and their change is more critical for the carbon and carbon cycle change. So now this capability has really come up. Okay, so here we compare the estimates against other available 5 such global estimates and our previous estimate to show that the revised methodology and data set have a better predictive capability. Okay, so the such spatial maps, if we could generate at a decadal or 5-yearly interval, they would really be able the direct measurement of how the carbon cycle or the carbon stock on vegetation is changing. But what actually happens is there is more carbon in the soil than in the vegetation. Now, up to now, the community and the soil scientists have been using only the soil map based estimates. This is one such estimate made for India in 2000. Now, if you follow this approach, then the land use, land cover, or any change, more productivity, nothing will change. The soil carbon pool, it will remain static. But now we know as the productivity changes or as other things happen or deforestation changes, the soil loses or gains organic carbon. So we need alternative methods of estimating the soil carbon density as well as the spatial map of this carbon. So there we have used again independent sampling and estimation through a CHN analyzer to and distribute the samples forest as well as the agriculture area and then make a model using machine learning, right? And then create an independent soil carbon estimate. So I will just show you the parameters where we have used the land cover, temperature, rainfall, soil depth, soil type, irrigation facilities, rock type, right? And created through a random forest model the prediction of the organic carbon as well as inorganic carbon, because soils have carbonates also. So then this then creates India's first 250-meter resolution soil organic carbon stock of 1 meter and inorganic carbon stock of 1 meter. Okay, so the numbers and maps are now then there. You can use also have the aggregated data output as part of the NRSC NICES program. But then now the global community has also moved to machine learning and the soil carbon mapping with point data. So there, what basically the two recent works I will show you. One is Reddy et al. Have used around 1700 of the soil mapping observations and created for 3 depths the soil carbon percentage. Because if you just use the carbon estimates, you will estimate a gram per kg or soil carbon percent, but not the pool. For estimating the pool, you must know the pores fraction and the bulk density, because these two are very important parameter to convert the concentration to the total stock. So they have only mapped the proportion, not the bulk density or the pores fragment fraction. Okay. The other is the international soil research organizations as well as the FAO through participation. They also have now created a 250-meter soil map. Now the issue is the methodology remains the same. The answers are different. What is the cost? The input data which is going into it is very less. Incidentally, in one of these maps, there are only 200 points over India. So obviously, this is a data limited issue. So since it is so much data limited and India really is a very rich in data, we just thought, let us use or develop a methodology of using the soil health card. You may be aware that Government of India has issued a soil health card to 140 million farmers, or 140 health card locations have been issued. It's really a big data. So we are trying to develop techniques and also harness this data to really create a very dense soil organic stock map. Because this is done at multiple times, it is done with multiple cropping systems. This will allow us to really measure and estimate different cropping practices and agricultural practices, how they have impacted soil carbon, and then how they are likely to change over time. So this is just the initiated work. I just thought I will put the other. The second one, as we said, FSI has been mapping forest cover since 1989. But carbon cycle is much longer. There have been earlier attempts by Flint and Richard. They combined 1880, 1920 and 1950 forest cover, but didn't really create a spatial map. So we concentrated as part of NCP to really do 80-year mapping of the forest. So 1930, 1975 and 2013, we really created using historical topo sheets, other data and current remote sensing, a forest cover map, which is now shown here as fraction of the forest in 5 by 5 kilometer grid. Then we have also created a forest type map, which then indicates what is the maximum biomass it can. So this then allows us to really not only map the changes, because there is a cycle of loss as well as gain, and it goes on varying at various spatial locations. So since you are trying to aggregate over entire India, you should be able to consistently map also the carbon, the forest changes over entire India. So this has been a very important contribution. So what then we have been able to do is to not only do 1930 to 2013, but use Markov chain model to predict spatially what would have been the carbon spatial map of carbon in 1880, or what would be the map, let us say 2025 or so. So these spatial maps and modeling as a back trajectory and forward allows us to generate the forest spatial cover scenarios in different climatic zones and parts of India. Now, there is a wide range of the variation in the carbon emission due to deforestation, because the biomass are different and the various carbon estimates were different. So what this NCP will lead to is, it will lead to normalize over this 100-year period, better estimate of forest carbon loss as well as the biomass. But this is one such early work where we showed that if you have only over the 5 regions in the country, the forest cover at multiple time, and then you use a bookkeeping model and use a depletion or recovery period of 30 years, what would be the carbon emission? What you would really see is that carbon emissions rise, and then after 80s they decline, because Supreme Court banned the logging and the deforestation in 1980s. So policies can have a strong impact, but there is an uncertainty because we really do not know whether this carbon loss during the earlier period, what has been due to deforestation and what has been due to forest degradation. That is why a remote sensing based better forest carbon is there. So this is another example of the same use of the forest density and carbon area changes to map the stock changes. I do not have enough time to really do, but you would really be covering fluxes towers. But NCP also established flux towers, because when we started, there were not too much data. So that is why the NCP took it upon itself to establish flux towers for plantation at Haldwani and Sal forest and Barkot, in teak forest at Betul, a mangrove forest in Sundarban, also Sal forest at Kana. Also we measured the fluxes over agricultural sites at many places. Now the IITM and Dr. Supriyo are over a past decade, they have under the MetFlux project also established flux towers in the Assam, in Darjeeling, as well as other places. So there will be discussion, but I just wanted to show you that this is one of the early results of how the total carbon flux of almost 3,000 gram carbon per meter square annually has a respiration of 2,400 and a net carbon accumulation of about 500 grams per carbon over this plantation site, which is in the sorry, this is a Sal forest in Barkot. In fact, most of the earlier estimates are much less because they only have worked on the main stem increment as a measure, not the overall entire ecosystem. The second one, this is the Betul forest, which over 7 years of data with some gap is shown here, and 5 years of the full year data again shows 524 gram carbon plus minus. This actually is much higher by the global standards. So this other published studies and the Betul are plotted in the side panel as you would see. So we are hoping that these observations would really help us in really resolving the real carbon stock as well as the uptake studies. Okay, but then parallelly using the satellite data and the photosynthesis model, one can compute GPP and NPP. There are various formulations depending upon what is your light use efficiency and what are the scaling factors of light and water stress. So we have used them multiple to really predict that there are positive trends in the NPP over India. And then if you see the net ecosystem, it means GPP to NPP to NEP. NEP can be positive or negative depending upon a drought year. This is a modeling framework using the CASA model. Now there are many such models available. What we have also been able to show is that this could, if you put it in a biosphere model, also lead to accumulation of the soil organic carbon. But this have not been independently verified. Now, what do you do for the NPP before the satellite era? So here what we have done is we intercompare three models, the Miami model, Schur and Thornthwaite, which are basically temperature, rainfall and ET based models with the modest data. We would be correcting, developing a machine learning based model so that not only for in the satellite era, in the pre-satellite era, we could really have a spatial map of the primary production. Okay, this workshop is devoted to synthesis by inverse modeling through use of the atmospheric CO2 concentration. We also have looked at the same issue. The inverse modeling strongly depends upon what are the spatial fields of the stock, respiration, etc. that you give to the inverse modeling. So different inputs can really produce different results, but some of the inputs what we generated here, they were put as part of the terrestrial exchange. So inverse modeling is a very powerful tool, but always remember that it is the improved spatial fluxes, ocean terrestrial, as well as other parameters, which are very critical for getting a correct answer. So roughly, our estimate is that the peninsular India had a land uptake of 60 teragram, whereas the northern India, that grid is a much larger, had 150. This is running over a 10-year period. But then I'm sure there would be more results, new results, better analysis, and other things which would be available. I have really covered my 45 minutes. I would like to stop here saying that we continue to work on better degradation, use of LIDAR data, better GPP model, also include Earth observation based solar induced fluorescence to improve the photosynthesis. and we would also adding the geospatial and history to really do over 100-year or a century scale the terrestrial carbon changes. Thank you very much. If there are questions or comments, I would request Vinu or somebody, they can look at the chat box and we could answer them. Thank you.
Thank you. Thank you, Dr. Dadwal, for presenting a very nice and interesting talk on Indian carbon cycle studies. Now this session is open for question and answer.
The question answers are asked via chat. So there are a couple of questions asked in the chat. I can post it to Professor Datwal. So one question is how carbon sink is determined when concentration changes rapidly. So this must be a question from one of the participants. How carbon sink is determined when the concentration changes rapidly?
I am not really sure I've understood the question. The soil organic carbon pool doesn't really change rapidly. There is a labile component, but then there are stable component also. Forest stock does not change rapidly. Wood remains, So I think perhaps what is being talked about is in terms of atmospheric concentration. As far as the soil or the vegetation stocks are concerned, they are there and they are stable. So you can estimate the stock size at 2 times and see whether the carbon is getting accumulated.
Okay. There is another query by a participant. Can we get all the AGB plot, the 2000 super plots mentioned, wise data? That is the query. Can we get the AGB plot, super plots mentioned, wise data, CBH and height? So is that possible to get?
As of now, data is not published, but I am encouraging all the PIs to really put up a full paper and publish. But they have many of the PIs, at least 30 of them, have published for papers where they have given lat long and the mean carbon density of that plot. So I think we could really put up those individual PI papers for that. But the estimated biomass 5 kilometer averaged is directly downloadable from the nicest platform on the Bhuvan for both soil and biomass. That is available.
Okay. So Supriyo, any other questions have you collected?
I saw one question that what was the inversion? So I think geoschem was used in this question.
Vinu, is there any question on YouTube channel?
Suprita, the one question is there in the chat box from Imran. Can you read?
This is how frequently do we need to calibrate CO2 flux measuring devices mounted on flux tower?
The closed ones are calibrated, I think, almost on daily basis. The open ones are ideally, I think, maybe bi-monthly or so would suffice. Other people may have more experience.
There is one more question. How many flux towers we have in India and how are they distributed?
Oh, in fact, in India, if you really talk to the people who have supplied flux towers, they say they have supplied more than 60. We had only 7. Supriyo has 5. Some agricultural universities have. But what I understand from the agents who sell the flux tower, somewhere number is between 60 to 70. But whether all of them are functioning, active, and collecting data, we don't know.
Actually, I just like to make one point here. In IITM, we have also purchased several sets, but other than the MedFlux project, the Kypex group also uses on campaign mode. So some of the flux observations are available, but only for short time by this Kypex group at IITM.
Okay. Yes, I think Dr. Prabir has put up a question.
Yes.
Dr. Prabir, it appeared on the screen and then went away.
Yeah, I can read this. Yeah.
Yeah, please.
I am curious whether we can produce land use change maps at certain intervals, say 5 or 10 years.
5 years is definitely doable in the era of the remote sensing. And I think before 80s, we could perhaps do 10-year also. But before 1920, we would really have to create modeled speculative decadal map. It is doable. Definitely, I feel it is doable.
Yeah, so I think that's one thing I think would be very important for the international community, because as you also showed in your presentation that like a FAO does not know, actually we don't, they have not so much data, but I think the people in India have so much information. This should be very useful for us to produce such thing, and probably NRSA is the best place to do this, I think.
Yeah, I saw some question in the ML. The ML errors are between 10 to 15%. RMSE is 10 to 15%.
Thank you very much.
Professor Dadwal, I have a question. Hello?
Yeah, please.
I could not write in the chat box, so I thought of asking you. So first of all, thank you for this nice presentation and on the overview of Indian carbon cycle. So this is Promit Dev from IITM Pune. So I have a question regarding the soil organic carbon. So you showed us the soil organic carbon map. So my query is, how does the soil organic carbon density or the total amount affect the soil albedo? And in addition to the actual carbon storage, how does this affect the climate change? Because when we talk about climate change or the carbon sequestration in plants, we talk of two contradictory effects, counterintuitive effects. One is the direct albedo effect, which actually does the warming. Another is the carbon storage, which is actually removing CO2 from the atmosphere. So how does these two play in case of soil organic carbon? Thank you.
Okay, first what we need to remember is the soil organic carbon is the total size with depth. So there are estimates of top 30 centimeter, top 1 meter, and even top 1.5 meter. The soil albedo is the top layer effect. So normally, if the organic matter increases, the reflectivity goes down. So albedo is lower. Same if soil is moist, albedo is lower. And if the soil becomes saline or there is a deposition, albedo is higher. But the point is vegetation cover strongly modifies this soil because what fraction of the soil is visible for albedo goes on changing by vegetation. But on the top layer, whenever there is a organic matter increase, the albedo goes down. Irrespective of the type of soil, the going down will be least in black cotton soil. It will be more in the alluvial Indo-Gangetic plains.
Okay.
Yeah,
Thank you so much. And in addition to that, since you talked about the carbon nitrogen ratio, so if we add more soil organic carbon to the soil, maybe agricultural or maybe forest soil, how will it affect the carbon nitrogen ratio and the immobilization and mineralization of nitrogen, which actually will affect the total carbon cycle?
So basically, it is a function. The organic matter has a one C and N stoichiometry depending upon whether you are a leguminous vegetation or non-leguminous. Then this reworking is done by the arthropods and earthworms, where they add their own proteins. Then the microbial organisms break it. So basically, it is again a function of the mean stoichiometry, which remains stable depending upon the geology and climatic conditions. Like acidic soils have different CN ratio, more aluminium means it will be slightly different. So I don't think the C to N ratio is going to change very dramatically. Even if we add more reduced nitrogen, there would be volatilization and ammonia formation.
Thank you so much.
Yeah.
There is one more interesting question posted by Dr. Krishnan. Which areas of India have witnessed increase in forest cover recently?
Okay, so if you look at FSI data, they have shown even Tripura, some areas had an increase. That is due to rubber plantation. See, there are small spots where afforestation and other things have led to the forest cover increase. Also, if you really, even in an urban area, if you take a newly urban area and revisit the outskirt after 20 years, you would see the tree fraction has increased. But it is, the issue is just a tree map is not sufficient. The amount of growing stock and carbon is critical. There the data and observations are not there. And I think Dr. Mahesh has talked about the CO2 calibration. He would really, there was a question on the calibration of the CO2. He's our colleague, ex-colleague from NRSC. He would really, I think, answer that query. He wrote on the chat box, P. Mahesh, on the calibration of the
Dr. Dadwal, I have one question regarding this forest cover. There is some debate that whether it is increased by forest, woody forest, or it is by agricultural fields. So can you please comment on this?
The point is, what has increased is the tree cover. So tree cover includes the block plantation and agroforestry, as well as trees alongside the river, canal, roads, and so many things. And if you take forest, the Indian legal definition is if 10% is covered by canopy of an area. So it means in a 1 hectare, even if 10%, that is classified as forest. So we should not only talk of the forest or tree cover, we should talk whether it is open, whether it is dense, moderate dense, or heavy dense. So other than the area, we should split it sub-pixel wise into fractional tree cover and count the cumulative canopy cover area. So as we do get more and more data, I think there will be refinement of definitions as well as the estimates.
Yeah, there is one question by Aparna Ravi asking, can you please point out which among the existing vegetation models work better for Indian region?
Models means, I mean,
which among the existing vegetation models work better for Indian?
So there are various type of vegetation models. There are DGVMs, there are primary productivity model, and there are biosphere model, and there are vegetation model as part of land surface processing. Now, and the satellite based models. Among the DGVMs, what basically is happening is those which have agriculture and dynamic phenology are better. Within the NPP, GPP, etc., those which are able to put the scalars for temperature and moisture stress, they work better. So as a thumb rule, wherever the phenology or water stress or the soil conditions can be brought into computation, those models will perform. So some formulations don't have this. Some formulations have this, but then are limited by absence of data. The model is there, but you specify constant data. So then it doesn't work better. So I believe still it remains as a data limited problem. Formulations, there are dozens of models available in all flavors.
Okay, thank you. Supriji, over to you.
So I think now we are running out of time. So there are a few questions and some of our related technical questions. I think we can discuss those questions in more detail during the specific presentations and during the hands-on session. So probably we can have a few minutes break before we start the next session, which will be coordinated by Dr. Praveen Batra.
So thank you, Dr. Supriya, and thank you, Dr. Vinu, for helping.
Thank you.
Thank you very much.
Okay, and thank you, Dr. Krishnan.
Okay, so we have the next speaker in line. So Prabir, can you put up this slide and take 2 minutes break?
Yeah, Nivasan will put up the.
Yeah,
so
Prabir, you can take over the session now.
yes, what do you plan? Like you take 5 minutes break?
We will take a break. We'll flash the first slide on the screen and take
Okay.
break. Yeah.
5 minutes break? 5 minutes?
Yeah, 5 minutes would be fine.
Yeah, because I think we can, still slightly getting into the lunch break is okay. Lunch break is enough. Yeah, right. And we'll have no queue in the lunch place, so we save time.
Okay, so we'll meet at 11:05.
Yeah.
Okay, so participants, please remain online. We'll take a short break of 5 minutes.
Yes. Good. So,
yeah, maybe you can talk to Dr. Niva and whether his slides are okay.
Nivasan, can you check your slides?
Yeah, can I share my screen
Yes.
now?
Try. If there are any issues, you can solve it. Oh, finally the sun is out. The morning was very cold here. Oh, good.
Can you see my slide?
Yes, it looks very clean.
How about this one?
Yeah, very nice.
Yeah,
okay.
Good. Yeah,
thank you.
Yeah. Just keep it like that. So.
Hi, good morning, Nivasan. How are you?
Yeah. Good morning and good afternoon.
Yeah, good to see you after a long time.
Yeah. Long time no see.
But when Vinu left, Nivasan was more in MRI, right?
No, he was at MRI, I think, for a year or so when I was there in Nice. Then he moved to Nice.
Yeah.
After you?
Yeah, after I left.
Good. I think so. I think there are a lot of materials from this. I think question and answer we can take it for the panel discussion and the afternoon discussions. Prasenjit is asking about calibration gas. I mean, this is an important issue, I think, for many people want to know about calibration gas. So, is there any Yogesh or anybody talking about calibration gases in the hands-on?
We have not included, but yes, we'll do it. It is a very good topic.
Yes.
So, yeah, so we will include it in hands-on.
I think in panel you don't need that. I think panel is not important, I guess. Or you can have briefly in panel.
Yeah, right. Yeah.
I think more for the users to know how important is that green and that calibration gas. People often don't realize it. They don't see it, right?
Yeah, exactly. So maybe probably we will discuss with all the groups who are doing monitoring the calibration procedure and then calibration type what they are using.
Yes,
and this is required just for the data accuracy.
So, by the way, I told you, Nivasan has a baby recently, so he's Nivasan already. I mean, Vinu already left, I guess, for a break. So we just give 30 seconds. So, Binu, are you there?
Yes, Prabir, I'm back. Yeah, let us start. Yeah, please go ahead.
Okay, I think let's start. So let's welcome to welcome to everyone to the core technical session. The so far we had a very nice overview talk from Dadwalji, and then I think now we can be more specialized talks, and you can, and this will be about, we'll be mixing the many talks in different ways, like atmosphere, land, ocean, and like that. So now the talk will be by Yosuke Niwa, and he has been working in this topic for a long time. So I think I would not want to take much time. I think I will ask Niwa-san to maybe introduce for a minute or so about his past research. And yes, the floor is yours, Niwa-san. Please go ahead.
Thank you very much, Patra-san. And first of all, I'd like to thank Bini-san and other people who organized this wonderful workshop. And I'm very honored to be invited as a plenary speaker. So hello from Japan. I'm working at National Institute for Environmental Studies, and previously I worked at Meteorological Research Institute, also this institute in Japan, and the collaboration with MRI is still ongoing. So in this talk, first I'd like to introduce global carbon cycle and inverse modeling briefly. And then I'd like to talk about Contrary project, which is an aircraft observation project conducted by Japanese groups. And then I'd like to introduce our inverse analysis system named Nismon CO2. And finally, I'd like to introduce our recent studies using Nismon and Contrary to estimate fire-induced emissions from equatorial Asia during 2015. I'm sure you know greenhouse gases are rapidly increasing. These numbers are the atmospheric concentration in the atmosphere from greenhouse gases, carbon dioxide, and methane, and N2O from pre-industrial level to the 2020 year level. For CO2, it was increased by 150%, and for methane, it was double, more than double, 262%. It increased, and also nitrous oxide is also increasing by 123%. So these increases are induced by anthropogenic emissions, for example, fossil fuel emission, land use change, and also for methane, gas leaks from oil and or industries, and also methane that and to increase are caused by agricultural activities. And for carbon budget, so CO2 problem, we emitted fossil fuel emission and line change by more than 10 petagram carbon per year. And however, in the atmosphere, 2.4 ppm is the concentration of atmosphere is increased by only 2.4 ppm per year, which means 5.1 petagram carbon stored in the atmosphere. So the rest of the carbon was absorbed by terrestrial biosphere and oceans. So each number is 3.1 petagram carbon to the terrestrial biosphere and 2.8 petagram carbon to the oceans. So terrestrial biospheres and oceans are mitigating the increase of carbon dioxide in the atmosphere. So this figure shows the time series of carbon sources and sinks by each component. Fossil fuel emission, land exchange, ocean, and terrestrial. The last part is accumulation in the atmosphere. So you can see from the pre-industrial level, the fossil fuel emission is rapidly increasing, and also the uptake by terrestrial biosphere and the oceans increasing as well. This is caused by the increase of CO2 concentration in the atmosphere. So this uptake process are natural processes, but this increase was caused by anthropogenic activities. In near future, we don't know whether these uptake kept increasing or not. So better understanding of saltiness sink mechanism in these reservoirs is imperative for precisely predicting the climate changes. In terms of CO2 sinks and sources, we have various kinds of data, and these are used for infer spatial temporal variations of CO2 fluxes. The left top figure shows the fossil fuel emission, which is from ODAC database, and the top right figure shows the fluxes in the terrestrial biosphere. These data are simulated by the terrestrial biosphere model. And the bottom left figure shows the biomass burning emissions derived from satellite observation. And the bottom right figure shows the air-sea flux map, which is based on a shipboard measurement. So we have this data set, and another approach to infer spatial temporal variations of CO2 fluxes is use of observation in the atmosphere. So to link surface fluxes with atmospheric concentration, we use a transport model. So in our study, we use a transport model named NICAM-TM. NICAM is a non-hydrostatic exohedral atmospheric model, which has been developed by a Japanese institute for a long time, and this model is originally aimed for super high resolution simulation to resolve cloud convection. But in our field, we apply this model to a greenhouse gas transport model. And into this model, we input this dataset, prescribed flux dataset, and also we input a meteorological dataset. Here is an example of transport simulation of carbon dioxide. And you can see the spatial variation of atmospheric concentration in the atmosphere, and this is the time series of concentration at this site, Minami Torishima. It is also Japanese ground-based station. So now we can perform with this model to simulate concentration in the atmosphere. But when we compare this with observations, we can see some discrepancies. For example, we see larger seasonal amplitude in the observations, and also increased growth rate is different between the observation and the simulation. In this figure shows the simulation showed much larger growth rate than observations. This means that the data set we input to the model is insufficient to simulate atmospheric concentration variations. So budget is not closed. So that is why we use inverse modeling. So this is very simple schematic equation of inverse modeling. The top equation is for the simulation, so that I showed previously. So we use source sinks data set and transport model. We obtained variation of concentration in the atmosphere. This is for the simulation. But meanwhile, in inverse simulation, we input observation into the model and we obtain certain things. So this equation is very simply described. So please note that this notation is mathematically wrong. Actually, we perform very complicated equation in the practical inverse simulation. So this shows how the CO2 observations look like. So the left figure shows the radio zone network used for weather forecast. We can see very dense network worldwide. On the other hand, we see very sparse observation network for observation of CO2 in the atmosphere. So this is because a high precision measurement is required. So it is not so easy to expand the network like radio zone there. So therefore, we have very many data gaps in space and also in time. Therefore, we are conducting wide coverage observations using commercial aircraft. So we use commercial aircraft, and we installed measurement equipment in the cargo room, like this picture. This program is named Contrail. This project is a collaboration with NIS, MRI, and also with Japan Airlines, JAL Foundation, and JAMCO, which is also a commercial company. So we have two types installed in the cargo room. One is automatic air sampling equipment, which collect air sample from the atmosphere during the flight. And another one is CO2 continuous measurement equipment. So this measurement only observes CO2, but it can measure concentration continuously during vertical sections and also horizontal sections. Here, this figure shows the flight route map of CME measurement. We can so you can see very wide worldwide network of CO2 measurement network here. Actually, some route is already stopped, and some is ongoing, but we have many various kinds of region data we have so far. And because this measurement is very high frequency, as I'm sure you know, aircraft fly one point to another place, and come after a few years, aircraft come back to the airport. So very high frequency measurement can be done by in the Contrail project. So a large number of data is available now, so we can perform this kind of analysis. This figure shows the vertical axis shows the potential temperature, and the horizontal axis shows the equivalent latitude, and the color shows the concentration. So this figure shows the concentration gradient in the UTLS region over Eurasia. So this map, this figure made by this route. And also we have vertical profiles in many places from those vertical profile data, we can make figure like this. So the vertical axis is pressure, so height, and the horizontal axis shows the equivalent latitude. So we can see a clear two-dimensional cross-section of CO2 like this. And that is global scale analysis. And here is a little bit local scale analysis. So this is done by Umeada-san, our colleague in the control team. He analyzed CO2 vertical profiles from CME measurement obtained over Delhi airport. And we found that even in winter, so this is January profile, we found a very low concentration near the surface. This means that during this season, some uptake process is existing near Delhi. So Delhi is a very big city, but this uptake exceeds the magnitude of urban CO2 emission. So it suggests a very strong sink existing here. So this is a temporal variation of excess CO2. So the positive means this type of profile, and the negative shows this type of profile. So during from January to March, we observed a very low concentration event like this. So after some analysis done by Umeada-san, he found that this strong uptake is attributable to active uptake by the crops grown in winter. This is a very interesting feature obtained by our observations. Such CO2 measurement of control, so the the recently international flight is dramatically reduced by the pandemic situation, but fortunately we the control observation is somehow ongoing. Even in 2020, this figure shows the flight route map of 2020, and some route is already stopped, and we don't have a flight to Delhi anymore, but still wide coverage is kept recently, and this flight destination from January to December 2020, and this year we have very plenty of data between Japan to North America, mainly USA, and this data set is already available from our website. So if you are interested in, please download them and try to use. So there are two categories. The data from 2005 to 2019, this data are provided as DOI, this number. And the latest one, this is a very preliminary data, is available from this DOI number. So another type of observation of control is flask air sampling, and we have very various kind of flight routes as well. From 1993, this air sampling measurement have been conducted between Japan and Australia, and unfortunately this line is already stopped, but this line has long history, so more than 20, almost 20 years long record it have. And also another line we have studied, so over Eurasia, this line started in 2012, and also recently we have many flights between Japan and Asian countries, Shanghai, Bangkok, and Singapore. So now I'd like to introduce our inverse analysis using Nikam TM. In this study, we used CME measurement, so continuous CO2 measurement data, and this is already published in 2012. In this analysis, we divided the globe into 40 regions and estimated proxies for each region. Then we found that adding control data, we obtained a very significant error reduction in South Asia and Equatorial Asia. So in Equatorial Asia, we obtained more than 60% reduction, and even for South Asia, we obtained more than 30%. So this strong error reduction rate is attributed by strong vertical air motion, which is typical air motion in the tropics. So this is a tag CO2 trace estimation, and we put proxies onto South Asia. And we can see very strong upward air motion into the upper troposphere. That is why fluxes are effectively captured by the control measurement and strongly constrained flux estimate in these areas. This is estimated flux time variation of from January to December. This is fluxes for South Asia, and the blue one shows the posterior fluxes using only surface stations, and the red one shows the results obtained by surface and contour data. So adding contour data, we obtain very strong uptake during a wet season, and this strong uptake was confirmed reasonable by comparing with independent aircraft data from Caribbean, which is a German aircraft observation program. And this study, this result was also consistent with the previous study of Patra-san, in which the Caribbean data were used in the inversion tool. And recently, using this Nikam TM, we have developed a more sophisticated inverse analysis system named Nismon. In this system, we use four-dimensional variational method, so-called 4D bar. So 4D bar, we estimate a high-resolution flux by using a large number of observations. This is because a 4D bar can deal with a large dimensional problem in which there's no limit in the number of optimizing parameters and observations. And this is a schematic figure of cost function, very simplified figure, so two-dimensional cost function. And in the Fodeba calculation, we seek optimal estimate by iterative calculation from the prior estimate like this. And the bottom figure shows the example of Fodeba estimate. The left panel shows the prior estimate, and the right figure shows the true estimate. So, and after the inversion, we obtain very flux. We obtain flux pattern like this, which is very similar to the true fluxes. And so, like this, we can estimate high resolved fluxes by this method. And recently, using such sophisticated inverse analysis system and also using control data, we perform inverse analysis to estimate fire-induced emissions from equator Asia. In this analysis, we, in addition to the control, we also used ship measurement data. This ship measurement is also conducted by our colleagues in Nice. And this study was published this year. So previously, many studies tried to estimate fire-induced emission in 2015. This is because in this year, a big El Nino occurred, and this area experienced a very dry condition. So due to such severe drought, a large number of fires occurred, and a large amount of carbon were expected to be emitted into the atmosphere. And some studies used MOPIT SHIO or SHIO and aerosol observations, and also OSHO2 carbon dioxide measurement. But our study used INST SHIO2 observation. So our study is the first study to use INST observation to estimate this fire-induced emissions. Fortunately, in that year, CO2 observation by control was conducted very frequently between Japan and Singapore. Right figure shows the vertical profiles of obtained over Singapore, so from January to December. So very good temporal coverage obtained by control observations. So how observation done is like this. So this is animation of control measurement, and the color shows the concentration of actual obtained concentration in October 2015. The top figure shows the vertical profile over Haneda, and the bottom figure shows the vertical profile over Singapore. So we can see very high concentration compared to Japan were obtained over Singapore, like this. And also we used additionally used shipboard measurement data, and this observation observed not only carbon dioxide but also carbon monoxide. So carbon dioxide, as you know, can be used as a proxy of fire-induced emission. So this is the animation of shipboard measurement. So ship is run like this, and so here very high concentration of observed near the Borneo Island. This might be contributed by fires. So to utilize carbon monoxide data in estimation of the fire-induced emission, I added CO function to the Nixon inverse analysis system. Detail skipped here, but we input carbon dioxide data to the inverse system. Then we also calculate carbon monoxide, and this atmospheric simulated concentration of carbon monoxide can be compared with shipboard measurement. Here is a comparison with simulation with observations, and we performed several sensitivity tests in the inversion, and four of them are in four experiments. We only used contour data, and so therefore, in this experiment, we can use shipboard measurement as independent of the inversion. And from this statistical analysis, we could confirm that these inversions reasonably performed, and by adding the contour measurement, we obtain a better agreement with a shipboard measurement. So these are the fluxes map of the obtained fluxes, and the right figure shows the numbers of fire-induced emission and the total net flux during September to October in 2015. And these are several from priors and several experiments.
Please mute your mic.
Yeah, please mute your mic, please.
Thank you.
Thank you.
Sorry for the interruption.
No problem. So the last row number shows our best estimate of total net flux and fire emission. So finally, we obtain about 300 teragram carbon from this very short term period. 300 teragram carbon is a very large number. So this is almost similar to the Japanese emissions, annual emissions for 2019. So this is summary of my talk, and I don't talk much about this, so I stop here. Thank you very much.
Okay, very good. So we have many questions for you. One thing is that the first question is from Sudip Chatterjee. You mentioned that trace gases are also measured by contrail. What are the trace gases you measure?
So in my presentation, only carbon monoxide here, and we can see a very clear signal from fire-induced emission during 1997. So another very big El Nino event. And other species, we measure SF6 and methane, and maybe sometimes methane isotopes, which already published by Umeda-san. Maybe you can find that paper in the Contour website. And yeah, principal greenhouse gases and related species we measure.
And then the question from Santanu Haldar. Aircraft continuously change latitude and longitude with time and altitude as well. How do you match the simulated concentration with observations in inverse modeling?
For comparison with aircraft? So actually, it is very good, and we already compared with simulation with continuous measurement, maybe 10 years ago, which is in collaborative study with Patterson and other modelers in Japan, which was published from SCP 2011. Yeah, very. Our transport model well performed spatial and temporal variations in the upper troposphere, and very comparable with continuous measurement. But still, we found some discrepancies. For example, over India, that's why we obtained very different flux patterns by adding control in the inversion. And this is after the inversion, we can see very good agreement with simulation with red one, and aircraft data is gray one. So after the inversion, we obtain very good agreement.
And then one other question from Vaishnavi Pandey. What should be the altitude of observational aircraft?
Altitude.
Not what you measure, but not where you measure, but what should be the altitude of observational aircraft? I don't know that I understand your question correctly, but it's like what would be like idealistic aircraft observations?
Idealistic observation.
Like what is the most effective measurements by aircraft? Probably the question.
Ah, I see. I think one prominent feature of our project is observing vertical profiles over each airport. Vertical profiles can be have very many information of fluxes, surface fluxes. That is very good observation, we believe, and also even high altitude data, we believe they are very good to estimate surface fluxes, because especially over continent, fluxes soon uplifted by a strong vertical motion. So even in the upper troposphere, our data is very useful to estimate surface fluxes, especially near Asian region.
And next question is, what were the errors generated while performing measurements with control? Like uncertainty, data uncertainty, maybe?
Data uncertainty of model?
Observations, I guess.
Observation is very accurate, we believe. Officially, the accuracy is 0.2 ppm, and the flux measurement is much higher precision. So such small error is not so problematic. But in terms of inversion, maybe we have to think about representative error of model. So model resolution is not so high, but observation is very high resolution. So we have to care about representative error of atmospheric transport model. For example, over near airport, so aircraft of the very high resolution, a high concentration near the airport. This kind of high concentration cannot be always reproduced by the model due to the representative error. So we have to care about such kind of problem.
So Binu, do you want me to continue or you want to take a break for 15 minutes?
I think we can continue. There are interesting questions. Maybe we
Yes,
can
I thought
take
so, yeah.
okay 5 minutes because discussion and break is what total 15
Yes,
minutes.
yes. So let me
So
continue
we
until
have
10 more minutes.
45 to 12 o'clock, 11:45 to 12. We can continue discussion and 5-minute break at the end
Yeah.
is fine.
Good.
Please
Yeah.
continue. Yeah.
Yes. So the next question is from Anju. Anju from SPL. What is the true flux mentioned in slide 20? Maybe in the OC yes. Slide 20.
Slide 20. So this one.
Yeah.
Yeah, actually, in this experiment, we prepared true fluxes in advance, and we generate pseudo observation from true fluxes. And using incorporating pseudo observation, we perform inversion. So true fluxes is a kind of arbitrary fluxes, which is different from prior flux.
Yes. So in other words, like you have the flux, you run through the model, and you have the concentrations. So those fluxes are for those concentrations are true flux. Basically, yeah. So can I get the details of people involved in atmospheric greenhouse gas measurements in India? So that maybe Niwasan does not know. Not many people he knows maybe, but yeah, I think that kind of information you can get from the discussion in the afternoon. So in the hands-on program, I think we'll know a lot of people who are doing measurements, and we'll probably meet them personally and discuss. So I'll skip that. Why do we have large seasonal offset between observation and simulations post 2008? I think slide 10 or 11 from Prasenjit Ghosh, IIS Bangalore.
This one?
No, slide 10 or 11. I think that the place when you're explaining the inverse modeling, because there is a data in that model observation gap. Yeah.
This one?
This one, yeah.
Yeah. This is
next one. I think next one. He's asking the next
slide
one.
9.
Yeah, you explained.
This one.
Yeah, that one.
Yeah, this is because the prescribed data input to the model is not sufficient. So budget is incorrect because each flux data made independently from each other. So summing them cannot always meet the observed growth rate. So that is why different between observation and simulation.
That is why we do the inverse modeling.
Yeah.
That's the whole reason of doing inverse modeling, because we do not have the full understanding of the carbon cycle on the land, in ocean, and also for the fossil fuel sometimes. So this inverse models helps us to sometimes identify the right reason for the right region why we miss something. So Vishnu Thilakan. So is there any plan to include other airlines in Contrail program, which will cover other parts of the Indian region?
Yeah.
Flying JAL to Chennai or Mumbai?
Actually, we are doing this project only with Japan Airlines, and it is very difficult to invite another air companies. And also, we cannot choose aircraft install the measurement equipment, so we cannot fully control the measurement line. That's why we lost the measurement to Delhi now. So in future, if Japan Airlines make some aircraft planning to go Delhi, in which our measurement installed, we can restart the measurement over India. And another thing is that IAGOS project, which is very similar project, but conducted by European group, they are doing a similar observation project and measuring carbon dioxide and other species. And they started recently, and I'm not sure, but they may cover another region. And we hope South Asia as well. So IAGOS and the country is compensating each other. So in near future, we can have a truly global coverage of aircraft observation network.
Yeah, so and maybe just to add that, so you may not, many of the people do not think about that the aircraft measurements are happening like in this kind of map, what Nyosan is showing, that it is going everywhere. But actually there are like a few aircrafts. Japan Airlines may have thousands of airplanes, but only 5 or 6 airplanes are equipped with these instruments. And those aircrafts has to undergo all testing by the Boeing company, and it takes like 1 to 2 years and millions of yens, maybe even longer, many millions of yens in cost to install this, and with all certification that aeroplane safety is not compromised. It's a huge task, and those who does it, like Inyosan and other people in the group, those who does it, they don't have to do it again. If they and then new aircraft model comes, for example, Boeing had 737, then the Boeing 7, whatever the 7, the newest one is 777 or something. So any model change of the aeroplane, you cannot transfer the instrument. You need to take a new certifications, everything new, and for any specific aircrafts. It's a huge task. So, but I think some of you should be able to do that in the future. Yeah, just to let you know. So yeah, next one is most important question. Is the model used here NICAM TM open source and freely available?
No. The answer is no, but we can provide the code personally, because the original model NICAM is also used worldwide, and I think some Indian colleagues are already using NICAM. So please contact us, and under term of the condition, you can use our model.
And so we have kind of 5 minutes. 7 minutes left. I'll skip the instrumentation part by the Gayatri Sirodkar, because that will be discussed in the later in the online hands-on things. So from R. Krishnan, are the fluxes over Africa in Nismon CO2 are due to biomass burning?
Africa?
Yeah, so that maybe the global map, that one.
No, global map. So emission estimate over Africa?
I mean, there is a global map, I think.
No, not this. The Nismon slide.
Yeah, in the early on. So.
Yeah. Previous slide.
Yeah, this one. Yeah. Where you saw the prior fluxes, I think.
Next one. Can we go to next slide?
The prior flux, like 2 slides. Yeah, that next one. Next one.
This one.
Yeah.
Yeah. For posterior July, you see a big.
This one.
For
previous one. Previous slide. Yeah.
This one. Yeah.
Posterior.
July, you see a lot of fluxes. What is it?
I didn't look through detail about this, but this may be contributed by biomass burning emission. In this case, I think I used data from GFEDO, which is very famous biomass burning data. So maybe that could be, yeah, one cause of this high emission in this area.
Yeah, so that's kind of a emission hotspot problem, yeah, from the biomass burning and also deforestation.
Yeah.
So people say that there is a hotspot in those areas.
Yeah.
And the ecosystem model has those information. Sometimes they produce those emissions in source regions.
Yeah,
and
but
next
yeah.
question from our Krishnan is that whether Japan aircraft observation EG from Japan Airlines are being shared with operational weather prediction centers.
Operational center.
I think they do, right? Under the WMO schemes, I think they are shared. The aircraft also measure this temperature and humidity and some other things, right?
Yeah.
I think those are actually probably shared with the weather prediction centers. I think they're under the WMO system, and I think JMA probably.
Yeah. Basic parameters like temperature, pressure, wind, speed, such kind of information automatically delivered to the JMA, Japan Meteorological Agency, and also maybe WMO to distribute worldwide. And our project carbon dioxide measurement is independently measured, and is not included in the data for weather forecast.
Yeah, I was just wondering, because if we also share the carbon dioxide data with the weather prediction centers, maybe in the future some reanalysis data sets may be able to produce these products, all these emission fluxes. So in the long term, because all these centers are revising the reanalysis data sets, so that may be an important source of these fluxes in the future.
Yeah,
yes.
In future we hope so. Yeah.
Yeah, in WMO there is a program now. I mean, it's going on for several years, but it is not really like a completely operationalized. There is a IG3 IS. I think Yogesh is now the scientific steering committee, and so there is a plan, like there is a system to probably archive some data sets, and it is bound to happen in the global stock take stage. So they will be not operationally, but I think we will provide the flux information, or whoever is asked to provide the flux information, they'll be available in some database, and it has to be transparent and easily accessible. That's what I think first criteria of the global stock take.
Yeah,
it's going to happen sooner than later, I think.
Yeah, because the future is going to be all these reanalysis data sets, maybe another 20, 30 years down the line.
Yeah.
So if we want to really go back and see what has happened in the history, so they will become very important. Yeah.
Yes, it's a very good point to end with this talk, I think. Thank you, Niwa-san, for doing excellent talk.
Can I ask a question?
Who speaking?
Can I this is Promit here.
Promit, can you not put it in the chat box?
Actually, I cannot see the chat box. It doesn't show me the chat box. So
you should find out. You should figure out with somebody's help. That would be very useful.
Yeah, I asked Dr. Vinu, but it's not available for me.
Anyway, quickly go ahead. Quickly go, because we are now running time is in 1 minute.
Yeah. So these aircraft measurements that you have shown, are those similar to these instrumented aircrafts, like what FAM uses in UK, or like they go to the different levels? I mean, are those suitable for the long range measurement, like what you have done using this commercial airlines?
So I couldn't catch clearly your question.
I think we need to stop because next speaker is waiting, right? I think I will. Sorry, Pramit. I think we have to move on. You can discuss offline with him by email or something. Okay.
Yeah.
I think. Thank you very much. And let's move on to the next speaker. And we do not have break, probably, right? Vinu?
2 minutes. We
2
can
minutes?
break.
Okay, 2 minutes break. What's the problem with Pramit now?
I will figure out. I will work with our technical team.
Sir, Prabir sir, can I share my screen and then you can put it up for the people?
Oh, you want me to do that?
Yeah, like that what you did, no? Because we will save some
No,
1 minute time.
It is shown by Nivasan directly. You can show yourself.
Okay, so I can I share? Yeah.
Yes,
I will share my screen.
Yes, please go ahead.
Okay. And then I will put up my presentation. Is that visible now, sir?
Coming. Yes. Go
Is
to
that okay?
Go to presentation mode.
Yes, I have already.
No, I mean that's the what is it? The display setting. I think that it is coming with your on speaker's note. You want the full screen.
Yeah, I am clicking on that, but it is not.
Yeah, there is one button you just select there. Try again.
Yeah, I will just stop sharing and then do it again. Wait 1 second.
Yeah.
So for me, it is looking full screen only here. Somehow. Okay, I will check. Screen. Okay. Is it on now?
Not yet. No, you actually are not showing the PowerPoint window.
Okay, just 1 second.
Because
is it okay now?
Good. This is good.
Is it okay now?
This is good. Perfect.
Yeah. Okay. Fine.
But you are seeing your outline slide, so maybe that.
Okay, just 1 second. Yeah. I will. But why is it showing something else for me? I don't know.
We are seeing the outline slides.
No, the thing is, whatever I'm sharing, it is not coming in here. Just 1 second.
Yeah. Sometimes this technology is not helpful, but yeah, we'll make it work. That's why you need the gap between the talks. So. And I think that if you go to that, I think taskbar or somewhere, can you see the display setting? Can you see the display setting?
Maybe you can try full screen now. I think this should work. Yeah.
No, that outline. This next slide is showing, right? Next slide. So go to the display setting here on the top. You see that there is display setting. Yeah. So swap presenter. Yeah. Swap. Yeah. Swap. Yeah. No. Yeah. Yes. That's good.
Yeah.
That's very good.
Very good. Yeah. Also, can you click that that button hide? There is a bottom banner is on your monitor. Yeah. That hide. Can you please click on it? Yes. Then do whatever you were doing earlier. Good. Very good. Please keep it there. Thank you. So Prabir, maybe 2 minutes we can break and.
Yeah, no, I am okay. I don't need break, but I think just we'll start in 1 minute.
Yeah. Thank you.
So Philip will join after lunch, right? Yeah. So, okay. I think we should start, go on to the more measurements talks. And Chaitanya will give us an overview of the measurements of greenhouse gases initiatives in India. I think there are a lot of questions about this one. So who else is making measurements, etc. And I think you'll also find many details about the measurements types and the precisions and the term and the difficulties and all the things. So slowly all these things will come up in this presentation. And I think Chaitanya, you can start your talk. The floor is yours. Thank you very much. Chaitanya, are you there? Chaitanya, are you there? Hello.
I think he has taken 2-minute break.
And also, but our screen is also frozen, right? Somehow.
No,
Yes.
I think his shared screen is gone.
Okay.
Yeah.
Okay, we are seeing his screen. Okay. That's why I'm moving very oddly on his screen. So.
Yeah.
Chaitanya called up me some issue. We are working on it.
Okay. Maybe it's needed, then we can show the PowerPoint for him, and then he can just speak.
He's logging out and logging in again. Hold a second.
Or we can
Chaitanya, are you okay now? No. I think you should be okay. I can see. Okay.
Looks like you can, if you try to unmute, you can unmute. Yes, you can try to do unmute now.
Yeah, so that looks fine now. I will try to sharing my screen. Yeah. Is that okay now?
Yeah, we can hear you, but the screen, yes.
And then about this presentation also?
We are seeing the team screen, but not PowerPoint screen.
Why? So okay, then I have to.
Yeah, this is fine. Correct.
Is that okay now?
Yes.
Okay. Please go ahead.
Okay,
Thank you.
I'm really sorry because there was some technical glitch. I could not unmute myself somehow. Okay,
Yes,
so thank you for what I was starting with. Okay, I should thank the IITM director Krishnan sir and the local organizing committee, Dr. Valsala, Yogesh Tiwari sir, and Supriyo Chakravarti sir, and Prabir Patra sir. As he has mentioned, Prabir Patra sir, the greenhouse gas training program, first one, I was the beneficiary of that. So I attended that, and now I'm here overviewing the Indian initiatives of greenhouse measurements. So I thank the opportunity. Because it's an overview talk, I made it a little bit general. I'm not going too much into the technical details of some of the things here. So just an overview, what are the things happening around India in terms of surface measurements of greenhouse gases. And then we will see in the later sessions, I think about more on the instrumentation, data analysis, calibration, and all. There are different sessions later. So this is just a general overview of the GHG measurement initiatives for India. And the outline of my talk, I will start with the importance of this already discussed in the previous talk. So I don't spend much time on that. We all know what is the importance of GHGs in climate change. And then sources, I'll briefly touch upon just for the completeness of the talk. And then how we go ahead with the GHG research. And then what are the different GHG measurement approaches, and then highlights of GHG measurements over India. And then Inaugural also we have started where I come from. So we have started GHG measurement initiatives recently. I'll touch upon that a little bit. And then finally, the takeaway messages from GHG measurement efforts over India. Coming to the importance, we have already seen, this is the IPCC 6th assessment report where they have already given the list of physical drivers of climate change, comprising carbon dioxide, methane, nitrous oxide, and so on. And then we see that the global scenario, we know, so it is continuously increase of these greenhouse gases that creates the problem or the issue, what we are looking for. And then when we differentiate between the natural and human drivers, we see here the natural drivers almost not changed much, what I could say. Wherever the human drivers, so you can see that there is a one-to-one correlation here. As the CO2 rises, the global temperature also rises. And then in this forcing estimates also, you can see that there is a huge contribution from the human activities of the human drivers. So that is where the issue comes in. And then coming to the major emission sectors for the greenhouse gases are like industrial, electrical power stations, transport, waste disposal, residential emissions. So there are many other sectors are there. Out of the greenhouse gases, the majority are taken by these three: carbon dioxide, methane, and nitrous oxide. Out of that, carbon dioxide is again dominating with 72%. And then methane is around 20%, and nitrous oxide is on 5%. And if we see the global emission scenarios, so India is also coming among one of the major contributors, along with China, US, and EU. So there is a real concern about the global carbon emissions from India, and then Indian government has already agreed that we will for the reduction of carbon emissions from Indian region in Paris Agreement, as well as the recent COP26 agreement. Also, we committed for that. So that makes those greenhouse gas measurements in India very, very important for us. And then now coming to the sources, so we see that this is the carbon cycle. Already the previous speakers have explained that. So the carbon exchanges. Sorry.
Yes.
Yeah.
I can see
the carbon cycle.
You posted something. I can see that. Yes.
Yeah. So
thank you.
Is that okay, sir? Hello. Hello.
Please pick up the microphone, audience.
Chaitanya, go ahead. Yeah, Pramit, just mute.
Yeah, I'm sorry. Yeah. So the carbon cycle we have seen already is that we have the exchange happens between the atmospheric gases, oceanic carbonate, and organic materials, and then non-living remains. So there are different processes which facilitate the cycling of the carbon in the atmosphere and biosphere and this one. And then coming to the carbon sources, when it comes to the organic molecules like CO2 gets fixed by the plants or the vegetation, and then when the vegetations are fed to the animals will respire to release the CO2 into the atmosphere. When it comes to the oceans, it will be the more of the fixing, and also a little bit of release and fixing is there in the oceans. And then coming to the methane, we have the main ruminants as well as the wetlands. Through the methanogenesis, they produce the methane into the atmosphere. Once the methane is in the atmosphere, it goes on oxidation to form carbon dioxide. This is the main reason we see that the methane levels are lesser than the CO2. However, the methane global warming potential is higher than CO2, but the methane emissions as such, or methane concentrations as such in the atmosphere are less because of this oxidation process, which will again contribute the CO2 into the atmosphere. And then the main culprit of the human activities is the fossil fuel extraction and then use in our combustion vehicles, transportation, and other energy sectors. We produce the CO2 directly into the atmosphere. For example, what happens when we burn the fuels is I have taken one example here where the propane combustion, you will end up in CO2 and energy and the emission of the CO2 directly into the atmosphere. N2O is majorly the agricultural soil management is the major culprit for the N2O emissions. We have seen that fertilizer use and other stuff will produce the N2O through oxidations, and then N2O will be released into the atmosphere. Now, coming to the greenhouse gas research, general terminology what we use in the greenhouse gas research are like concentration, XCO2, XCH4, net flux. When I attended for the first time this greenhouse gas national training program, I was unaware of the differences between them. So now I know, so I thought, okay, that would be better because there are a lot of students and early stage research career researchers are there in this program as well. So it is better. The concentration, when we say the concentration, it is the in situ measurements. Normally the gas contained in a certain volume of the air that we all know. When we talk about the X CO2 and X methane or X any gas, so that is the satellite measurements actually. So this is to differentiate between the in situ measurements and the satellite observations or retrievals. We use the term X in before that species. And the next part is the net flux, which is the difference between the amount of gas added into the atmosphere by the emissions of various sources and also taken away from the atmosphere through the sinks or the fixing mechanism, which will remove the gas from the atmosphere. We call that as the net flux. Here is an example for the X CO2 and X methane in the global level. You can see that there are three different global, northern hemisphere, southern hemisphere. So all these retrievals we could do, and then we can see that when we compare with southern hemisphere, northern hemisphere, we have the more prominent seasonal cycle because of the terrestrial vegetation. And similar for the methane, we can see that in the beginning of 2003 to 2006, there was not much increase in the methane, whereas after that, the methane started increasing back again. So these kind of retrievals we could do using the satellites, and this gives an example for the X CO2 and X methane, whatever I was talking in my previous slide. And then coming to the net flux, which is the other one. So the net carbon fluxes are very large, as we have already seen in the previous talks, and then generally they are measured in gigatons. 1 gigaton is nothing but the 1 billion metric tons. So you can see that the mass of the carbon cycled every year. So the yellow ones, whatever mentioned in this or denoted in this picture is all the natural processes, wherever the red ones are the the human influence or the fossil fuel, cement and land use, so the human activities or the anthropogenic emissions. You can see that there is something like the net 9 gigaton of carbon is added and distributed among the atmosphere, something like 4 gigaton and 3 among the on the photosynthesis and then 2 among the ocean fluxes. So you can see that there is a added carbon burden on the atmosphere cycle every year. So that is the reason we see that there is a steady increase of the greenhouse gases or the global carbon increase, which is leading to the climate change problem. However, it is very difficult to directly measure, as Prabir Patra sir said already. So it is very difficult to directly measure the size of the carbon sinks and the fluxes between them. Instead, the estimates are made using a term called inverse modeling. Previous speaker has already explained what is inverse modeling. It is an approach we use to estimate the net fluxes by linking the increase in the atmosphere about their sources and sinks. So we put up all the data, atmospheric concentration measurements, satellite retrieval data, and then prior fluxes, meteorology, atmospheric chemistry, transport, everything goes into these models, and then we try to estimate that. This approach combines an accurate in situ measurement, concentration of the gases, and then knowledge of how they are transported and mixed into the atmosphere and the chemistry in order to get the underlying fluxes. So here is an example I have taken from the Copernicus Atmospheric Monitoring Service. You can see that they have estimated the net flux of global net flux for the CO2, methane, and N2O. Net flux, you can see that the net fluxes can also be converted into the global growth rate of the CO2, something around 2.2 or 2.4, whatever we have seen already, ppm per year. So in a nutshell, the GHG research approach is that we have the in situ surface measurements or the surface measurements and then satellite retrievals, and then we add the meteorology, sources and sinks information or the emission data, and then transport, atmospheric transport and chemistry into the inverse models, and then that will give us the estimate of the net fluxes of these greenhouse gases. So that could be used for climate forcing estimates later. Now coming to the GHG measurements, so in the global, we have the WMO Global Atmospheric Watch network is there. We can see the network around the globe with the objective of obtaining global distribution and trends of GHGs with sufficient resolution to provide quantitative estimates of regions, sources and things. And then how do we do the surface measurement calibration? According to the WMO guidelines, there is a central calibration laboratory, which is NOVA GML. They provide us the primary standards, which are like, the recent, they will, time to time again, they will re-look into the concentration, accuracy and all. So recent paper in 2021 April, which was published by them. That is the denotation comes from WMO CO2X, stands for the concentration of that particular cylinder. That is the recent 2019 update of that standard. And then we do use those things for the instrument calibration and drift correction. And then once the instrument is calibrated, we use that instrument to calibrate our secondary cylinders, or what we call it as working standards at the lab. And then we correct our measurements to the working standard. These secondary standards are traceable to the primary standards. Along with that, there are also thing called long and short target cylinders, which are, one is in the very near to the atmospheric concentrations of the CO2 or any other greenhouse gas of interest, and one is the above higher than that concentration. We try to get the response of the instrument by feeding them for a short period. Now coming to the satellite missions around the globe. So way back from 2002, there are different satellite measurements like Yamachi, GOSAT, OCO2, Transat, Sentinel, Profomi. So many missions have come up, and then from 2020 and then in future, recent immediate future also, there are many other satellite missions which are coming up. You can go to the respective space agency websites like JAXA or European Space Agency, NASA. So for more details about these things, so this is just a list I wanted to provide for the information purpose only. So there are many other greenhouse gas missions are lined up for the future satellite missions. And then how do you calibrate these satellite missions? We calibrate them using the upward-looking Fourier transform spectrometer network. It's called Total Carbon Column Observing Network, TCON, by Caltech. So the need of this network is to validate the satellite data. TCON measurements help to validate satellite data, and then that TCON network has become the Global Atmospheric Watch Program in 2009. And then calibration of these TCON instruments are made by the aircraft measurements as well as air core, which is nothing but the air sampling on balloon platforms up to stratosphere, and then offline analysis of those samples. On the respective sites of these, FTIR instruments, so they do the aircraft and air core measurements, and then they calibrate the FTIR instrument. So another network is there for the same purpose, upward-looking FTIR instrument that's called Network for the Detection of Atmospheric and Composition Change, which is endorsed by UNEP WMO GA again. And the major objective of this is similar, to establish the long-term databases for detecting changes and trends in atmospheric composition, and then validate the atmospheric measurements, and then to provide the validation support for atmospheric models as well as for the satellite retrievals. Now, this is a overall different instruments what we use in GHG research. For example, Tall Tower, where we measure the CO2 by putting the sensors on the tall towers, and then flux measurements, and then also remote sensing like FTIR, what I explained in the previous slide, and in situ measurements like NDIR spectrometers, CRDS, that cavity ring nose spectrometers, or LGR, which is a cavity enhanced spectrometer. And then also offline analysis you can do. You can grab the sample from the different sites and then bring into the lab, and then you can do the analysis using the gas chromatograph systems. So here what looks like a typical greenhouse gas research lab. You have the sampling systems, you have the analyzers which are measuring the in situ measurements, you have the the offline analysis gas chromatograph. So this is from the NOVA GML lab. So you can see that this is how the typical lab for the surface measurements look for. Now coming to the highlights of GHG measurements effort for India. I'm putting some of the important papers what I feel which contributed significantly to the measurement efforts over India. Before going to that, this is the updated list of different. One of the questions was there in previous talk. Who are the people who are engaged in GHG measurements over India? I think this slide will give the answer to that participant. So we have different stations established under different programs like NIOPRL project with ISRO, which was the earliest site, Cape Rama. Unfortunately, from 2013 onwards, there are no samples from there. And then ISRO GBP National Carbon Program, what Professor Dadwal was talking about. And then also MOS, IITM Pune observational programs are there. CSIR for PI and LSCE Paris joint program. And then also some of them are upcoming programs, what is atmospheric research test bed at Central India by IITM Pune itself. So there also the surface measurements are coming up, and also atmospheric observatory at Sonipat campus in IIT Delhi. That is another project which is coming up. Those are denoted here in the yellow. Other than that, these are the sites where the surface measurements are being carried out at the moment. However, there are gap areas. For example, in Indo-Gangetic plain, we don't have the measurements, and this part of India we don't have, and also Rajasthan region we don't have the measurements. So there are a lot of gap areas also. We will look into that later. Coming to the journey of the greenhouse gas measurements over India, this is one of the earliest reports. Of course, Prabir Patel sir is there. In fact, Yogesh Tiwari sir is there. So it is using the Cabo de Rama or Cape Rama observations. They have shown that it has provided the critical guidance in optimizing the fluxes to constrain the regional source and sink balance over Indian region. Noting the significance of this work, they are estimating the flux and balance of Indian subcontinent. They recommended establishing a network of long-term monitoring GHGs and their isotopic composition in this study. And then later, in 2013, there was a paper from Northeast India measurements, including the Bose Institute and others. So they have measured the methane, nitrous oxide, and sulfur hexafluoride in Darjeeling. That's a high altitude station in the Himalayan foothills. So the observations show large variability in and frequent pollution events in methane and N2 mole fractions, suggesting that significant sources in the region sampled throughout the year. Contrastingly, the SF6, which is a more stable component, show little variability and only occasional pollution episodes, likely due to the weak sources in the region. So thus, what they said is the variations observed in the Northeast India, that is in Darjeeling, are dominated by the large-scale flows or the transport rather than the local emissions. Next was by IITM, that is in 2014. They said that they studied the impact of Indian monsoon circulation over the CO2 spatial variability and using the ground-based monitoring stations of Cabo de Rama as well as Sinhagad, which is a station maintained by the IITM Pune. So they in this study, they said the impact of the Indian monsoon circulation on the surface CO2 over India. Continental and marine trace transport mechanism influence the Indian subcontinent. Lower CO2 events along with the west coast to India are due to the marine transport, and CO2 variability is around 8 to 10 ppm during the summer monsoon and 15 ppm for the rest of the year. Now coming to the another effort is that additional of new stations. It is the CSIR 4th and LSCE Paris joint program. They added 3 new atmospheric stations, one in Hanle, which is on the north tip of India, which is having less continental influence, or we can call it as continental background station. And then Pondicherry, there is a tropical surface station in the southern peninsula of India, and then also an oceanic station, Port Blair. And they have seen that the annual gradients of the atmospheric mole fractions in these stations suggest significant emission sources for the respective gases. And then measurements have potential to constrain the inversion fluxes over southern and northeastern India. And then they also suggested this network of ground stations needs further expansion. And the next paper was from western Indian region, Ahmedabad, where they have measured the CO2 and CO simultaneously in an urban setup in Ahmedabad city. And then they have shown that the usefulness of the simultaneous measurement of CO2 and CO in the urban region, the anthropogenic and biospheric components of CO2 have been studied. Its temporally varying atmospheric concentration and validity of the bottom-up inventory has been assessed independently. These results represent a major urban region of India and will helpful in validating the emission inventories chemistry, transport, and terrestrial ecosystem models. However, again, they said the bigger network is required. And the next reporting from the Deccan Plateau region, that is the Hyderabad region, from NRSC Shadnagar site by Mahesh and Srinivas et al. So they have used the surface measurements, and then they reported that the maximum CO2 is observed during the pre-monsoon, while methane recorded maximum during the post-monsoon. CO2 and methane show strong positive correlation during the winter, pre-monsoon, and post-monsoon, indicating a common anthropogenic source for these gases. And major sources for CO2 are the soil respiration and anthropogenic emissions, whereas the vegetation acts as the main sink. For methane, the sink is the hydroxyl radicals. The next measurement paper from them only, they have reported so that they have an FTIR instrument, probably the only FTIR instrument, upward-looking FTIR instrument from Indian region. So which they use for the retrieval of the satellite validating the satellite retrievals. At the moment, the achieved precision on the retrievals are something like 0.17 to 0.52 for CO2, 0.3 to 0.77 for methane, and 6.3 to 8.92% for CO, and 0.41 to 0.75 for the N2O. Against the TCON, what I explained in the beginning, recommended precision of less than 0.25% or less than 0.3 and 1 and 0.5 for CO2, methane, CO, and N2O respectively. The next most recent paper in 2021 in the Nature Scientific Reports by Yogesh Tiwari group by Methia et al. So they have again shown the effect of monsoon on GHG dynamics. What the key message they have come up with the study is that CO2 poses significant diurnal variations in monsoon and post-monsoon. However, methane exhibits a dual peak-like pattern in pre-monsoon. The study suggests that the GHG dynamics in the western region of India are significantly influenced by the monsoon circulation. And another paper from the IITM again. So they have measured the CO2 enhancement due to the Indian flux, the regional fluxes. The regions of enhancement greater than 0.2 ppm can be considered for the location of surface observations representing the Indian fluxes. Similarly, the regions with enhancement greater than 1 ppm could be covered by the satellite or airborne observations to discern the enhancement in the atmospheric CO2 mole fractions due to Indian fluxes was the key message they have given in this study. And then another paper from IITM by Supriyo Chakravarti and Mithya et al. So they have done the CO2 and methane and fluxes, and then also the isotopic ratios. What the key message in this study they have given is that the study shows the importance of source characterization when the concentration changes rapidly to ascertain the net ecosystem exchange in the flux. At NEE, partitioning was constrained by using the carbon isotopic ratios in this study. So, and then there are, as Professor Dadwal has already shown, there are a lot of flux measurement initiatives over India. And then this is the summary of all the flux measurements happened so far. I have taken from this report, Assessment of Climate Change over Indian Region by IITM. So we can see that the blue line here says that the sequestering or the removal of the CO2 happens mostly in the monsoon, and then in the central India and then eastern India mostly post-monsoon. Northeast part is pre-monsoon, and then this winter is mostly during the southern peninsula, southeastern peninsular India mostly during the winter. So basically this is very much dependent on the monsoon, because which would enhance the vegetation cover over India, and then the removal processes or fixing through the vegetation happens during those periods. So the main points what we could see from the flux measurements is flux measurements in Indian forest vary widely across the ecosystems. The Kaziranga forest in northeast sequesters maximum during the pre-monsoon, and then forests in Haldwani and Barkot sequestered during the summer monsoon. And then central India, again, I said post-monsoon. And then Pichivaram, that is the southern eastern part of India, where you can see during the winter monsoon. That may be because this region of India is considered as the rain shadow region. It receives the northeast monsoon most. So during that period, the vegetation cover will be higher here. Now coming to the NERL initiative, about the GHG measurements. Those who don't know about NERL is called National Atmospheric Research Laboratory under the Department of Space, an autonomous research body set up near Tirupati. And then we have different research areas focusing on radar application and development, ionospheric and space physics, atmospheric structure and dynamics, aerosol radiation and trace gases, cloud and convective systems, and weather and climate. So I belong to this group called aerosol radiation and trace gases, and then we have a climate observatory maintained at the site with comprising different analyzers on aerosols, radiation, trace gas instruments. I mostly take care of the trace gas measurements, including all the pollution monitoring instruments, greenhouse gas analyzer, VOC measurements, and then aerosol chemical characterization. So coming to the measurements of greenhouse gases, this is recently published in Atmospheric Environment, this work. So we have the NERL situation in India. We have shown that here. So it is in the southeastern part of India, where the measurements are done by Picaro and G2401 CRDS analyzer, and the calibration was done. Nova cylinder calibration was done at CSIR 4th Institute, India, for the instrument correction, and then we use the secondary cylinders at the site for measurement corrections frequently. And then we know the CRDS is nothing but cavity ring nose spectrometer has a cavity, optical cavity comprising highly reflective mirrors, which will retain the light, and then the residence time of the light is measured using photodiode. And when there is an absorption by the species like methane or CO2, that residence time reduces. By looking into the cavity residence time of the light with and without the sample, we can calculate the concentration of the methane by using the Beer-Lambert law. So it's an adaptation of the Beer-Lambert law only. So we have done that, and also this instrument is already recommended by the WMO also in saying that the precision of the instrument and the accuracy levels we get out of it. So this is the time series of the measurements from 2016 to 2019. We can see that there is a very huge variability of all the three gases, CO, CO2, and methane. And the black line here is the one what we have used as the minimum diurnal mean, or the 5th percentile method, just to have a background concentration of these species. And above that is the local emission impacts. And then when we calculated the trends for the background using the NOAA method, we can see that we have something like 2.5 ppm per year in CO2, and then 111 ppb in methane, in comparison with the global by the Mauna Loa measurements, slightly higher, which again because of the regional influence on these gases. And we can see that annual cycles, the CO2 and methane are influenced by the monsoon circulation here also. And then we try to differentiate between the local emissions and in the long range transport. We see that the excess concentrations, by subtracting the background, we can see that CO around 20-25%, up to 25% it is going. For CO2 around up to 6%, the CO2 excess is there depending on the season. And then methane also has something like 2 to 3% of excess concentration above the boundary. And then we try to understand what are the sources. In this picture here, we can see that the Modi's fire counts around the site. The center cross point is the site. And then these are the fire counts detected. We can see that there is a correlation. When there are higher fire counts, we have seen the higher concentration, extra concentrations of CO, which shows us that the influence of local emissions are there on the observations. And then this is the correlation between the excess concentration between different species to ascertain whether there are common sources or different sources. CO is not correlating well with either CO2 or methane, maybe because of the local biomass burning or something is the main culprit for the CO excess what we see. Whereas methane and CO2 have some correlations, excess concentration, indicating that there are some common sources, mostly with the transport of these species, because they are the stable gases. And then we have also done the polar plots along with the winds to see the correlation between the excess concentration we have seen and the winds at the surface. And that also shows that local influence is there for all the three gases. And to ascertain the long range transport, we have used the concentrated weighted trajectory models. We can see at different seasons in the site, we receive the winds from different places. For example, in the winter season, it is mostly from the northeast and then Bay of Bengal. And then during the southwest monsoon, June, July, August, it is mostly from the southwest part. And then during the summer, it is mostly the peninsular influence. And then during the post-monsoon season, we have the mixed winds coming from that. And then also we have done, because we have both the influence like southwest as well as northeast monsoon, and then the wind reversal happens somewhere in October. So just to give an idea how the wind reversal changes the air trajectories coming into the site, we have shown the flex part potential emission sensitivity maps here. So that gives the distribution of these air mass trajectories and then how they are influencing the concentration. And then also because this site is a boundary layer site, and then there are, in spite of warnings from many people about the surface measurements of the satellites and not to use the surface measurements of satellites for ascertaining the CO2 methane, there are some studies they have used the surface level concentration retrieved from the satellites for the scientific studies. We wanted to just give an idea how the biases are there and all. So we have taken the Gadanki, which is a boundary layer site, and then Mauna Loa, which is the above boundary layer site, just to show the biases between the surface level measurements from the satellites. We can see that CO, of course, is the low, the lesser lifetime gas, and then mostly influenced with the local. We have the highest bias for CO, and then for the CO2 and methane, the biases are less. But among the Gadanki and Mauna Loa, Gadanki biases are higher compared to the Mauna Loa, which again indicates that the boundary layer, measurements of satellites need to be considered carefully while looking into the scientific aspects. So the key messages from our study is that local emission and long-range transport impacts were investigated. CO found to the most local emission impact species among the three. Forest fire, agriculture residue, and biomass burning around the site were the dominant local sources. Trend analysis shows that significant decreasing trend in CO and increasing trends for the CO2 and methane, which is slightly marginally higher than the Mauna Loa values. That are the global values, and then comparison of the satellite data with surface measurement showed significant bias, so which indicates that we have to be careful while using the boundary layer measurements of satellites for these gases. So the key take-home messages from the GHG measurements efforts so far over India are that GHG measurements show higher seasonal amplitude, cycle amplitude as compared to the observations at Mauna Loa, indicating the strong local and regional biospheric activity. There is significant enhancement in GHG background concentrations in India due to the local and regional fluxes. Indian monsoon circulation has strong influence on GHG variability across India. Surface GHG measurement sites in India are still sparse in nature. In the absence of long-term observational records and comprehensive modeling and biogeochemical processes, there is a limited understanding of the dynamics of GHG variability in India, and to ascertain the driving mechanism behind this as well as long-term variability at country scale, a strategy designed network of long-term surface CO2 concentration associated flux observations are essential, which would help the expansion of the observational network as well as development of process-based biogeochemical and coupled climate carbon models may fill the knowledge gap. Such expanded capabilities would help to improve the assessment of the mitigation potential over Indian region in the future. So same thing has also been said in this second biennial update report, which was submitted to the United Nations framework by MOEFCC. So you can see that establishing an integrated domestic monitoring, reporting and verification system for ESG mitigation actions is a capacity building need for India. An integrated MRV system for GHG mitigation requires streamlined data management systems, technical capacity, improved analytical capabilities, and most importantly, active coordination between all the stakeholders, various nodal agencies within the government or across the region, sectors, and time is also a prerequisite to go for this assessment. Now coming to the challenges, what we are facing over Indian region at the moment, the GHG measurements, especially the surface measurements over Indian region, are the insufficient spatial coverage as noted by many studies. And also the calibration, there are no common reference stations or lab to carry out calibrations in Indian region. There is one reference lab in CSIR 4th Pi Institute in Bangalore, where they have the NOAA calibration procedure and cylinders, and they follow strictly. Other than that, we don't have any other reference stations. As many of you may be knowing already, getting the NOAA cylinders and then maintaining the reference lab is not that easy. It needs a lot of effort and a lot of coordination among different people. So that would be one thing we need to look into, how to calibrate our instruments, how to calibrate our measurements in a common platform so that our measurements can be comparable. And then also data processing training to the researchers, which is the main focus of one of the focus of this national training program also is essential. And then we may have to guidelines for specific instrument data processing, and we have to circulate among the researchers, or what is called as standard data processing procedure or something we may have to set up. And also, this is also there in the panel discussion theme later, the common data repository to assess in the national level scenario, common platform for data sharing and further studies using models would help ascertaining national level emission scenario. That is also another key area of concern we may have to look into when we are going ahead with the GHG measurement initiatives over India. So I think I have used up my time. So I will stop here. So definitely there are many other interesting talks like techniques used in India for the GHG measurements by Dr. Yogesh Tiwari sir will be very interesting or complementary to this talk, where you can see that all these measurements are carried out by using what different instruments and what calibration, how we do the calibration, what are the specification of those instruments, and all will be given by him. And also other data processing hands-on training and all will definitely help us in going ahead with this research. So thank you very much, sir.
Thank you very much, Chaitanya, for this excellent talk. I think you covered a lot of things, and yeah, hopefully many people will. Can you stop sharing this screen? That screen?
Yeah. Which one, sir? This. Okay, just 1 second. I will.
There. No, not this one. This one. Keep it there. Yeah. So there are obviously some questions. I myself one. When you calculate the greenhouse gas trends, the growth rate from a very short time period, because what are the effects? Did you do a sensitivity study to check how robust is the estimation of your growth rate for methane and CO2 from your side?
Yes, sir. I agree. I completely agree with you, because very short time, 3 years is not a big gap. So we just wanted to give it is a vague estimate. Actually, it needs to be refined, and we are continuing those instrument as measurements for the longer time now. So in the longer duration, we will refine. Definitely, we use that NOAA method where K is to that polynomial fit 2 for this less than 3 years. This one sensitivity check and all we have done, but still, it will not give you the real picture. I agree with you. So we will refine that later once we have the long-term data sets. So yes, that may change. So we have already mentioned in that paper limitation also. That is correct. Whatever you pointed out is correct. Yeah.
Now, because if you have so let's say you might claim that India emissions are increasing faster than
Yes, correct.
What we mostly see that there's an offset. So if you have more emissions, we mostly see an offset from the baseline.
Correct.
But generally, the concentration growth rate is similar, because this is so well mixed gas around the world. It just mixed in 1 week or maximum 1 month. Everything gets mixed.
Correct.
So
correct.
on the growth rate, I'm not sure. Actually, I don't even know. Like that's why I'm curious.
No, actually, what happened was there are some reports from Tibetan Plateau region in India. So they were also recently published. In that paper, we have quoted them. So whatever the growth rates we have assigned, calculated here, estimated here, they are comparable with those rates from the Tibetan Plateau region. So it looks like, I don't know, we may be off a little bit, but not very off from the growth rate. That's what we feel, but we will see that. So when we acquire the long-term data sets, definitely we will look into those things. Yeah. Thank you.
Yeah, good. So there are other questions from Eldo Elias. Among the list of the greenhouse gas stations, which are the ones that uses tall tower measurements?
No, tall tower, I don't think many are there in India. So only the flux tower, I am not very sure. Vinu sir, can you help me? Do you have any idea? Do you have any tall tower measurements in India?
Tall tower measurements in ARC Bhopal coming, na, Yogesh?
Yeah, coming. Yeah, that's what. But at the moment, we don't have any because I just want I put it in the general introduction of the GHG research there, not for the Indian thing, because those are the instruments we use in that. So that was a general information for those who are looking into this. That's actually in India. I'm not very sure there are many tall tower measurements.
Yeah, but I think this is a good point, I guess, because in India it's very difficult to find an background station.
Correct.
Which is not affected by the local emission, but still track the Indian emissions. Sometimes I've heard people saying that Hanle does not really see the Indian emissions. Because the Indian emissions moves in the different directions from Hanle. They don't go there. So,
yeah, that's our research also shows trajectories are totally capturing from the North African sites and all this Hanle signals coming.
Yeah, so it's a good point to consider and good discussion point, good question.
Correct.
So the next question is, can we use AIRS and GOSAT data in regional greenhouse gas as a special resolution each course?
AIRS data, but what we want for the, I don't think AIRS has stopped giving the CO2 measure, in this one now it looks like. So the CO2 data is not there in the AIRS. So what we wanted to show in this particular study, what I explained is that, there are some studies where they have used the lower pressure level atmospheric gas concentration of CO2 and methane for the pollution level studies and all. What we wanted to show is whatever the satellite sees for the lower levels, that may not be very accurate. Already there are many papers which are already citing these limitations because there is, the surface reflections play a major role in that uncertainties. So we wanted to show them just the kind of a quantification for that. So you have to be careful when you are using the lower level measurements of this. So that is the whole idea of this. Rather than the other part of that question is that on satellite retrievals, there are many other satellites which are available, so we can use them better because they are already better accepted in the global CO2 and methane community than going for. These are like trace gas measurement satellites, right? AIRS and all. So their main goal is not GHG measurements.
Yeah. So Prasenjit is asking you that you may have missed some of the papers from IISc. The question is, how do you take care of air propagation when you transfer calibration to the secondary cylinders?
No, that's what. No, so what we do is we go. Normally, I go with my instrument to CSIR 4th Pi reference station in near Bangalore. That's Hospitality, where we do the calibration of the instrument, and then we do the drift correction of those instrument measurements. And then we bring that instrument back here, and then we calibrate our secondary cylinders using that calibrated instrument now. Because the local cylinders, what we get, we don't get the precision like 0.1 ppm or something like that. We get in percentage, 1% or 2%. For example, 1% error on 400 ppm cylinder will be like, it may be 396 or it may be 404. We don't know that, what is the exact. So what we do now is we feed that cylinder into the instrument and then see the exact concentration of the cylinder. That is our secondary correction for that cylinder, secondary cylinder working standard. And then we use this cylinder for our routine measurement correction.
Okay, so Vinu, I think we'll go for next 5 minutes. Is okay?
Yeah, I think this is the last talk before lunch break. So we have a 1.5 hour break. So maybe a couple of interesting questions we can pick up from chat.
Yes.
Then
So
we can
I'll go until the 5 more minutes.
Sure. Go ahead. Yeah.
So there is a question from Professor Samlal. How growth rate at your location compare with others location in India, even though data are for short periods?
Growth rates that's what there are not many reports of the growth rates from India and actually because of the as mentioned in many studies, the record is very short, so not many efforts have been done. There was one paper from the Tibetan region which we have already compared with that, so those rates are really comparable, something like 2.4 ppm per year or something they reported, and then what we have seen is around 2.5. Again, I said it is only for 3 years, so we have to see that later what happens.
So Smriti asking general question. I am curious, like we have this talk about consolidated measurements attempts in India. Can you have a general idea about all the modeling groups information compiled in some talk? Like who is running what type of model? Okay, this is for not for you. This is for general.
And I agree. So because probably one of those, Vinu sir, you can answer that probably.
Where our more talks are aligned in day 3 and 4.
Yes. And so Smriti is there, so locally, so you can talk directly to him.
Right. I think the comment is very valuable. So
yeah,
there are talks aligned in this in angle.
So Imran is asking time series of CO2 at Gadanki shows variation from 400 to 600 ppm.
Yes, there's a lot of
values used in the train analysis is around 410 ppm. Is it
so
because
that is
daily minimum values or monthly means?
No, actually, it is not the daily minimum. What we have done is we have taken the the diurnal minimum. That is one of the methods, and also 5th percentile method in your ACP paper from. You are also one of the co-author in that paper, Chandra sir's paper. So we have used that method to ascertain the background of this one. On this background, we have used the growth rate, because including the local emission on the CO2 and measuring the growth rate, there is no meaning for that because we cannot do that. So this is even though the variation is huge in that, but when we take the minimum, the diurnal midday minimum or the 5th percentile, this is around that 410 ppm. So what we have calculated.
By the way, can you just clarify like your site in the site?
Yes, sir.
Your site is above the canopy level or is within the canopy level?
We have a terrain kind of thing, and then the measurements are taken on the top of a building, which is the instrument, and the sampling is around 10 meters height from that building is above the canopy level.
So you are measurements at the canopy level.
Sampling is above the canopy level. Yes, of course.
But just around the height of the trees, right?
No, because we are on top of a building here. So it is a terrain actually. Yeah, it is a terrain, and then it is a terrain. This is a mountain terrain actually. The building is already above the tree canopy, and then we are measuring from top of that building. We are taking the sample.
How tall is the building?
Sorry, sir. It is a 4-story building. 4-story building on a terrain. So somewhere around 35, about 35 meters. And then I'm around 40 meters from the ground level, if you call it.
Yeah, but I'm wondering, like 600 ppm looks to be very high. How do you get that?
That may be because because there are a lot of there is a nearby village is there around 250 meters from our site, and then they use a lot of agricultural waste burning, and also this site comes under the Eastern Ghat region. And during the summer, there are a lot of forest fire events are there. So we note those things, and then we will take care. But we don't throw away the data, because just to show that this is the variability we are seeing actually. So it is not that it is not. Yeah, that's what. Yeah.
You cannot throw the data.
Yes, yeah.
They're so variable, and we do not know where and what purpose it will be used in the future. So keep all the data, but
correct, exactly. But we have to be careful in interpreting the data. That's all I could say. Yeah.
And there's a little question. So I will skip Elias's question about the common database. I think those will come up separately.
Okay.
And have you checked the variation of boundary layer height at your site? And since you said it is a hilly terrain,
Correct.
can there be any possible effect of the valley wind and gravity waves, etc.? From Pramit Dev Burman.
I don't think we have not checked it, to be honest. But the thing is, of course, the boundary layer height is there. Height we have already mentioned it, but not on the front of that gravity waves and valley wind. Because it is not a exactly a valley. It is terrain in the sense. So one side we have the mountain, other side is almost flat. It is lands. Okay. It is not exactly like between the two mountains or something like that. So boundary layer variation is there, which has the effect on the definitely diurnal variability of the CO2 and methane. But gravity waves, I'm not very sure. We have not looked into that.
So you have to invite Pramit to your site.
Correct. Yeah, please. Yeah, always welcome.
Yeah, I think we'll close the discussion here now.
Praveen, I just like to make a comment.
Yeah, yes. Go ahead.
See, this is Chaitanya is here presented very, very nice talk and very comprehensive talk. But what I liked is that he came here first time and he said that he was motivated by GHG-1. So I would hope that GHG-3 will produce more such Chaitanyas in the future.
Thank you, sir. Thank you very much. Definitely. Yeah.
I want to add just one point. Chaitanya's last slide where he showed the gap areas and key points, they are very good for the panel discussions.
Okay, sir.
Very good, Yogesh. In fact, I have taken 2 screenshots, Chaitanya.
No,
I
sure,
will
sir.
flash it during the panel discussion.
So you can share the presentation if you want, sir. That's not a problem because most of that are reported work only. So I can share this presentation with you if you want. Yeah, please.
Very good, very good.
Yeah. Chaitanya, we are proud of you because from GHG-1 to GHG-3, you really learned a lot, and then now you started a site and producing a data. This is really great win for these workshops, actually.
Thank you very much, sir. Thank you. Thank you very much. Thank you very much for all the guidance because I was with his working group only when I was doing I attended that program. Yogesh Tiwari sir was our supervisor for data analysis, and whatever the NOVA methods what we have used was taught by him only. So I should thank him. Thank you, sir. So at least we could learn something. Yeah.
No, we are proud of you, and go ahead and then keep doing observations.
Thank you, sir. Thank you. Sure, sir. Definitely. Yeah.
Okay.
Okay, I think we should close this now and come back for the big talk by Philips here.
Yeah.
Okay. Okay.
So, Prabir,
thank you.
Yeah, Chaitanya, please.
So thank you very much for the organizers again, and thank you. Yeah.
Yeah. Yes. Thank you. Prabir, be there by 2. I mean, IST time 2:20 at least, so that we can test the Philip Kia's presentation. Okay. 2:30 we start.
2:30. Yeah. Okay. That means it will be like a 6 p.m. here, right? Yes.
I'm sorry I keep you so busy and
that's
no
okay.
break.
That's okay. It's only 4 days in a year. I mean, several years. So
okay. So for Indian colleagues, we will regroup at 2:30 for the talk, the keynote talk of the day. And until then, it's the lunch break, and you can come back at 2:30. Thank you.
Thank you.
Also, thank Prabir for chairing this session. Thank you.
Yeah.
Thank you.
Yeah. Bye.
Bye. I'll close it now.
Currently 13.
Hello.
Hi, Dr. Philip.
Hello.
Hello. Hello.
Yeah, I can hear you well. Can you hear me?
Yeah, we can hear you well.
Perfect.
Yeah.
Yeah,
Good morning
Dr. Philip.
and good afternoon.
Good morning, good afternoon.
Good afternoon.
So we will start in another 3 minutes. Please wait. So Yogesh, you are chairing this session, right?
Yes, yes.
Maybe you can ask Philip to load his PPT and see.
Yes, yes. Philip, can you share your PPT so that the first front page?
I will try. Let me see. Do you see my screen now?
Yes, yes, we can see.
Okay, and I will try to put it in full screen. Now, is it in full screen?
Not now. Yeah, maybe.
Okay, let me see. I'll try again. Can you see it in full screen now or not yet?
No, it's same.
Okay, so I'll try again. Maybe just sharing the screen should work. Is it better now?
Yes,
Yeah.
yes, perfect, perfect.
Can you
perfect.
move the slide a bit, one slide to see whether it's moving?
Let me see. Yes.
Yes.
It should work.
Good. Yes.
Yes,
Thank
yes,
you.
yes.
I'm sorry, I cannot activate my camera. There is a bug on my computer.
Okay.
But as far as we have the microphone, it should be okay.
Okay, perfect. Yeah, perfect. Thank you for joining.
And thank you very much for the invitation.
Yeah.
Hello, Professor Philip. Hope you are having a nice time.
Hello.
Yeah, I met you during the Swiss Climate Summer School in 2019.
Yes, I remember.
Oh, nice to see you again.
Nice to see you.
Yeah.
Okay. Shall we start? 2:30 now?
Yes.
Prabir is joined. Prabir, are you hearing us? Looks like we can't hear Prabir.
Can you hear?
Yeah, we can hear
Yeah.
you. We can.
Oh, sorry.
Yeah.
Hello, Prabir.
Okay,
Yeah.
Yogesh,
Hello.
please take us ahead.
Yeah. Okay, so good afternoon to all, and welcome to the afternoon session of GHG-3 workshop. And in this session, we have Dr. Philippe Sias with us, and he is going to give talks. So Dr. Philippe Sias is world-renowned scientist in the field of carbon cycle. He doesn't need any introduction. Almost all the people working in this field knows him. But as a customary of this workshop, I will just give some introduction about Dr. Philippe Sias so that the early career researchers should know about him. So Dr. Philippe Sias is currently Associate Director at the LSE Paris, France. He studied physics during his bachelor's and master's in France. He received a PhD in 1991 in the field of Holocene climate records of Antarctic ice cores. In 1992, Dr. Philippe Sias was a postdoc fellow at NOAA Boulder, Colorado, USA, and investigated how carbon and oxygen isotopes in atmospheric CO2 can be used to constrain terrestrial carbon fluxes. He also designed in the first three-dimensional simulation model of the heavy oxygen isotope in carbon dioxide. After 1994, Dr. Philippe Sias returned to France at LSE and carried out research into the inverse modeling of carbon dioxide and methane fluxes at the surface of the Earth based on transport models and a global network of surface in situ stations. Under his leadership, this activity has been developed at LSE into a research team. In parallel, Dr. Philippe Sias led the establishment of French greenhouse gas atmospheric monitoring network, going from 2 stations in 1992 to a network of stations today, and became a key component of ICOS large-scale European research infrastructure. He and his group have initiated GHG monitoring program in India at sites Hanle, Pondicherry, and Port Blair. Dr. Philippe Sias continued research during the last 20 years, mainly on the relationship between ecosystem CO2 fluxes and climate, combining terrestrial biosphere models with satellite and eddy coherence observations. He took part in the setup and interpretation of one of the first coupled carbon climate simulation with the IPSL climate model and pioneered the incorporation of cultivated ecosystem into a terrestrial biospheric model. Dr. Philippe Sias has been principal investigator of French, European Union and international projects and became a co-chair of the Global Carbon Project in 2009. He had the opportunity to contribute to several syntheses of recent trends in the carbon cycle, characterized by the recent fast growth of emissions and by a slowing trend of natural sink, a finding that had led a large impact in the media. He acted as a co-chair of the Global Carbon Observation Strategy of the Group on Earth Observation GEO Task Force on Integrated Carbon Observation. He has worked for the IPCC in the IPCC assessment reports. On behalf of Scientific Steering Committee and local organizing committee of this workshop, we thank Dr. Philippe Sias for accepting our request and giving a keynote lecture. With this, we welcome Dr. Philippe Sias and request please deliver your lecture. Thank you.
Okay, thank you very much for the invitation and for this nice introduction. It's a great pleasure to give this presentation, mainly about the comparison of the inventories of anthropogenic emissions of the 3 greenhouse gases with the result of global atmospheric inversion. And the paper is in discussion in Earth System Science data. So to start with, I think it is clear that after the Paris Agreement, emissions have still increased. They dropped significantly during the COVID pandemics, but we see them rebounding this year. And we know that we have now really a decade to see emissions coming down if we want to meet the goals of the Paris Agreement. And the current situation is that the pledges of different countries is not really adequate for following a trajectory that will prevent warming to go below 2 degrees or 1.5 degrees. So in this context, the Paris Agreement has set up a process through which the different pledges and also the emission declarations by the countries will be considered at successive intervals, which are called the global stocktake. The next global stocktake is coming up soon in 2023, and the second one will be in 2028. And it's stated in the UN documents that the process needs to be transparent in the light of equity and best available science, but it is still strictly party-driven, which means that the emissions that will be reported by countries will be very important to define the baseline upon which the pledges can be analyzed and considered. Yet, you can see that the timing is not ideal because, on the one hand, there is an enhanced transparency framework through which all the countries part of the agreement will have to provide regular inventories. But at the moment, it is not the case. We have only the so-called Annex 1 countries, which took part in the Kyoto Protocol, that have annual update of their emissions. And for all the non-Annex 1 countries, which today emit about 70% of the global greenhouse gas emissions, there is no regular reporting. So we are in a situation where the first global stocktake will have to be done with the best available science, and it's only in 2024, so after the first global stocktake, that we hope to see the first inventories being regularly reported by all the countries. We also expect that in many developing countries, the infrastructure to develop carbon or greenhouse gas accounting is not very mature. So we expect that the quality of the inventories that will be available on a yearly basis after 2024 will be very different, which will make the comparison of the different pledges more difficult. So in this context, well, we have on the one hand the official process of counting for emissions. First of all, I should recall that countries are only responsible for anthropogenic emissions, not for total emissions which occur in their territory, and not for, let's say, embedded emissions in the exported goods and products, for instance. And the main method of inventories is essentially to compute the product of activities multiplied by emission factors that give estimate of the emissions for different gases and for different sectors, which have been agreed upon by the IPCC guidelines. So the purpose of this study is to compare bottom-up estimations, which are reported by countries to the UNFCCC, with a different method, a method called atmospheric inversion, which is based essentially on the exploitation of the gradients of concentrations, let's say downwind and upwind a certain region, to infer a quantification of the fluxes of this region. And this is, of course, not easy because, as most of you may know, atmospheric inversions are a relatively complex system that makes a fusion between three types of information. Essentially, an inversion is a system that is going to find out what is the optimal set of surface fluxes that best matches some atmospheric concentration data. The atmospheric concentration data can come from in situ stations, but the in situ stations data are very precise, but they're also very sparse. Or they can come from satellites. Satellites offer a global coverage, which is interesting for countries which have few in situ stations, but it's also a relatively sparse observing system because the current satellites are mainly sounders, and they do not provide, let's say, continuous images of concentration, say, on a daily basis. The second ingredient of an inversion is an atmospheric transport model that relates the fluxes that are optimized to the concentration. So the quality, the resolution, for instance, of the transport model is very important if you want to go to fine scales, especially for relatively small countries. And the third ingredient is a first guess map, or what we call a prior guess, a prior map of the fluxes, which generally comes from inventories or scientific models. So all these ingredients being realized, it's possible to obtain a solution for the inversion. And of course, it's important here to consider that the solution depends, of course, on different settings, but in particular on the transport model. So that's the reason why we have used different global inversions, which have been published in the literature, mainly through the papers of the budgets of the three greenhouse gases They have been led by the Global Carbon Project. We use 6 CO2 inversions updated to 2019. They are all based on surface observations, except one that was based on the OCO2 satellite data. For methane, we use the inversions, but the last update of the methane budget only goes to 2017. And here we used 9 in situ inversions. 2 of them are also combined in situ with satellites, and 8 satellite inversions, which are using the GOSAT data. GOSAT is a satellite that is providing column concentration of CH4 measurements since 2009. Last for CO2, we used, in fact, I should say 3 different inversions, also updated in the paper of Rankin Tian in Nature, up to 2017. So in parallel, we have also done some work to try to compile a global dataset of inventories. This is not completely easy because, as I was explaining, for Annex 1 countries, you have standard reporting, a big Excel spreadsheet where you have emissions for each gas and for each sectors and subsectors, sometimes with a lot of details. Details doesn't mean quality, it just means that the format is harmonized, so it's easy to get the data. But for the non-Annex 1 countries, mainly all the developing countries and the emerging economies, we don't have regular harmonized inventories. We have 2 types of reporting. Some of them are national communications. They are periodical, but they are not regular. And the other type of information that is available is called the biannual update reports. It's generally a PDF document which contains a lot of information about adaptation, governance, biodiversity, but many PDF reports of the biannual update reports also provide a table with emissions. It's not necessarily complete. It doesn't have all the gases and all the sectors. This is how a CRF inventory form looks like for an Annex 1 country. You can see the detail of the different gases, sectors and subsectors, like for the energy, the manufacturing industries, or the transport. So they contain greenhouse gas emissions, but also removals in the land use sector. And here I want to point out that because countries had difficulties to assess what is really anthropogenic and natural on the land, because of course the process of environmental changes and human-induced changes on land use are completely intermixed, they decided to use a proxy, which is called the managed land. So they decide an area which is under management, and they count the emissions and removals of carbon dioxide and methane and N2O on those areas. And if there is an unmanaged land, it's considered as not being under their responsibility. And this is important for the rest of the presentation. Now, in terms of national communication and biannual update report, the situation is not so great because many countries did not provide any regular updates. You can see each line is essentially the number of national communications which is available. Mexico has 6 of them. Brazil, Ghana, and Armenia have provided 4 national communications over the last 15 years. But for 154 countries, there is only 1 single national communication which has ever been provided, and nothing else. And for a country like Iran, for instance, there is a single communication, which is for the year 2010, which is far away from the present period. In terms of biannual update reports, you can see also the statistics of reports. We have a few countries that provided many of them, like Andorra, Namibia, and Chile, provided 5 biannual update reports. But most of the developing countries provide only 1 biannual update report, which is in national language, in Spanish, Russian, or in Arabic, for instance. So this is a lot of work because a BUR looks like this. It's a PDF document. You can see it's very different from the CRF form of the Annex 1 countries. For instance, some gases are not reported here for the case of Mongolia. And the sectors are not always the same than the one which are used for the standard reporting. So what we have done, and if you compare here, for instance, Mongolia and Malaysia, you will see that some sectors are very detailed in the case of Malaysia for the industry, but there is very little detail in the case of Mongolia. So what we have done is that we have analyzed all these PDF documents, and we have converted that into Excel spreadsheets. We have done some clerical error checking to create a new database, which looks like this. Essentially, the color in orange is the number of years which are covered either by national communication or by biennial update report for each non-Annex 1 countries. And the blue countries are those that are providing, since the Kyoto Protocol, an annual report. Still, the annual report is lagging about 2 years compared to the current year. So you can see that for many countries, we have relatively sparse and infrequent reports, which is a problem, of course, because inversions are providing annual estimation. So what we have done first is a grouping of sectors, because you have many subsectors in national inventories, and in inversions, given the kind of mixing by the atmosphere, we lack this detail. So, for instance, for CO2, we can only solve for the net land CO2 fluxes, and we diagnose it in inventories so that it can be compared with what we see with inversions. And for the CH4, we grouped the anthropogenic emissions into two super sectors or categories. The first one is all the fossil extraction and distribution methane emissions. And the second one is a grouping of agricultural and waste, which we obtain by taking from inventories the sectors of agriculture waste, including indirect emissions, and all the emissions from these sectors, and we remove the field burnings of agricultural residues. So after this sectorial grouping, there is a next step to consider. It is the fact that inversions are essentially physical systems that capture all the fluxes, including the natural fluxes. And if you want to compare their results with the anthropogenic emissions from inventories, you need to do some corrections. In the case of CO2, the inversion returns a CO2 flux map for all the non-fossil emissions. The first step was to mask this gridded data using managed land, because inventories are only reported for managed land, and for that we remove from the inversion grid cells the unmanaged lands, taking mask from intact forest from Potapov and natural grassland from Chang et al. This is not ideal because countries do not report a map of their managed versus unmanaged land. They just say, okay, we have this amount, this fraction of unmanaged land, but they don't tell you necessarily where it is, at least not for all the countries. So we use those geophysical data to first filter the inversion for the managed land. And then we realized that there were a number of CO2 fluxes which are exchanged at the surface of the Earth that have nothing to do with anything which is measured by inventory. This is mainly the CO2 which is taken up by plants and channeled to rivers and escaping to the atmosphere from inland waters. Part of it is also transported to the ocean. We have also the uptake of CO2 by crops, and we know that the biomass of crops is processed and consumed by humans, so it's re-emitted somewhere else. And these fluxes are relatively neutral from the point of view of the carbon stock changes, but of course, they are seen by the inversion, so we corrected for this. And we also corrected the fluxes for the wood trade, so that in the end, we have a corrected CO2 inversion fluxes that can be compared with the national inventory anthropogenic land use sector emissions. The same was done for methane, because we have large natural sources of methane, in particular wetlands, inland waters, and also wildfires. So we use here 3 different methods to remove those natural sources to essentially extract the anthropogenic emission of methane that can be compared between inventories and inversions. We use different methods. The first one is essentially to trust inversions themselves and to trust their partition of anthropogenic versus natural. Still, inversions have a sector called biomass burning, which contains both anthropogenic fires, like burning of crop residues, and wildfires. So we remove the wildfire emissions using the GFED fire dataset. The second method is similar. Simply, we remove from the inversion the median of all natural sources instead of each inversion solution for the natural fluxes. And the method 3 is, again, a correction where we have to remove the natural sources, but in this case, we take only bottom-up estimates from scientific data for geological emissions, termites, wildfires, etc., and wetlands, and we remove them from the total inversions to essentially extract the anthropogenic emissions. For N2O, we did also a correction, removing the wildfires and removing the emissions which occur in an aquatic system. There is a nice paper by Han Kintian. And we took only the natural pre-industrial component of those emissions because N2 emissions from inland waters coming from the leaching of fertilizers, for instance, are counted as indirect anthropogenic emission in inventories. We also selected countries for making the comparison. It's difficult because a very small country, it's meaningless to compare an inversion result. Some countries have a lot of stations, others have very few stations, but they are still very important for the global carbon cycle because they have a huge population, large emission, or a lot of area of forest. So we made a compromise in terms of selecting countries that have some observation coverage, relatively large area, so that it is meaningful to compare with inventories, and which are significant for each of the three gases that we consider. This gives you an idea of the density of the observations for CO2, methane, and N2O, and the colors are noting the countries that we have analyzed. Of course, we analyzed all the countries, but the results are shown only for the countries which are in color. So as you can see, there is few tropical stations. So a country like Brazil or Congo are not well covered by the in situ network for sure. If you look at the GOSAT methane sampling from different GOSAT products, it's better, of course. GOSAT has a good coverage over the countries where we have few in situ observations. So it's an interesting observation system, but still there is a very different data density depending on the GOSAT products that we used. And the different inversions are using different GOSAT products. So now coming to the results, each of these plots is showing you the land use fluxes. When it's negative, it means that it's a carbon sink. The black dots are the inventories. So you have data every year for Annex 1 country, and for countries like China here or India, you have only the available national communications. So we start with the raw data from the inversion, the kind of average or median of the 6 inversions, which is the thin line. And then we apply a correction to essentially remove those lateral fluxes. So we go from the green dotted line to the green thin line. We start with the median of all inversion. Then we filter only the managed land. So you can see for Canada, for instance, if you reduce inversion to the managed land area, you have a smaller net sink. And then the last correction is the one which includes the lateral fluxes. So these lateral flux corrections are very important for some countries like Brazil and Canada, but they are not so, and India as well, but they are not so important for others. And what we found is that generally speaking, there is a relatively fair agreement between inventory reports and inversions. Inversions have a lot of internal variability which the inventories don't have, which is normal because the method to process carbon stock changes is mainly a 5-year revisit of biomass stocks, for instance, so it cannot capture internal anomalies. And we also found that for northern boreal countries, in particular Russia, but also the EU and Canada, the inversion sink was much larger, even after considering only the managed land, than the amount of carbon uptake which is declared in their inventory. Looking at India, you can see that there is, essentially the inversion is, the median of the inversion is relatively close to the inventories. It's a bit of a smaller sink compared to what is declared by the Indian government. The situation for methane, here I show you the total anthropogenic emissions, so it's fossil plus agriculture plus waste, is a bit more contrasted. For some countries or group of countries like the EU, the US or China, there is a kind of relatively good consistency between inversions and inventories. The light blue line is the GOSAT inversion, and the dark blue line is the in situ inversion. So of course, the GOSAT inversion only started in 2009. So generally speaking, and this is a good news because it's two completely independent observing systems, there is a relatively good alignment between the GOSAT solution and the in situ solution, except perhaps it's for China, a little bit for India. We have some slight differences, but they are not too large. And we can see that in many countries, in India, but also in Indonesia, also in Australia and in Argentina and Russia, there is a significant higher estimate of the median of the inversion. compared to the inventory. Still, the range of the inversion, what you see as the blue area is the range, the min-max range between the different inversions we have, is very large. But still, we can say that there are many countries for which we found a significant negative difference between the UNFCCC report and what we see from the two atmospheric observations. Of course, the way you separate anthropogenic from natural sources is critical if you want to compare inversions with inventories. And here you see how different are the anthropogenic emission of methane for different countries, depending on the method you apply to separate anthropogenic from natural. And the general conclusion is that, of course, the method has an effect. For instance, in Brazil, some methods are giving very different results. But for most countries, we still have a relatively robust way, I believe, to do this separation if you consider the differences between methods to split anthropogenic from natural across inversions. So now I'm showing one sector of methane emissions, which is the fossil emissions. Fossil emissions are big in countries that are extracting coal, oil, and gas, in particular in China, in the US, in the Gulf states. So we could not do, let's say, Qatar, for instance, or Iraq separately. So we grouped all those countries together. And here we found, interestingly, that in China, the inventory is higher than the two families of inversions. In the US and Europe, it's relatively consistent. Inversions are a bit above the inventories for Europe still. For India, it's also quite consistent, but you can see that the amount of fossil methane emission is very small in India compared to China. It's about 10 times smaller. But for other countries like Indonesia, but also all the oil and gas extracting countries of the Arabian Peninsula, and also in Russia, we found a significant underestimate of the fossil emissions of the inventory compared to the inversions. This is particularly striking for all the Middle East countries, but also for Central Asian countries that are extracting gas, like Kazakhstan and Turkmenistan. In fact, here you see another comparison table. In red are the inversions, and in blue you see the UNFCCC values, but also other scientific bottom-up inventories. There are many of them, EDGAR, IEA data, GAINS, EPA, CEDS. So you can see also the difference between bottom-up inventories. And it's quite clear that for Russia, for instance, the official inventory is a much smaller number than both inversions and other inventories. For the US, it's relatively consistent. For all the Gulf states, the UN inventory is very, very small emissions compared to all other estimation methods, top-down or bottom-up. And for the rest of the world, it's relatively similar. There is a significant underestimation by the UNFCCC self-reported emissions compared to both scientific bottom-up inventories, let's say, and the total of inversions. If you look at Russia, for instance, it's quite interesting because there is also a variation in the method that Russia is applying from year to year to assess its fossil methane emissions. And when they update their inventory, they change the method, and you can see there is a large variation. In 2006, Russia was declaring about 17 teragrams of methane, mainly coming from oil and gas and not from coal. Suddenly, their report jumped up to more than 30. Then it stayed high at about 25. And in the recent year, the Russian government has changed essentially the data, and they have cut their reporting by about a factor of 4. So this has to be considered because even though these Annex 1 inventories are very detailed, countries have the right to change the accounting method from year to year. And as you can see, in the case of Russia, there is a factor of 5 difference between different successive editions of the national inventories, and of course, inversions from GOSAT and surface network do not show such a year-to-year changes. So it means that the stability of the inventory method is in fact very critical, and we are unfortunately going to see more of that after 2024 when all the countries will start reporting annual data. This is a plot showing the methane emissions from another important sector, in particular for India, the sector of agriculture and waste. So you can see that here India is a very big emitter, of course, large population, very powerful agricultural sector. And we found here that for some countries like India, but also in Brazil and in Indonesia, in Brazil and in Thailand, the inventories was less than the inversions. for other countries like Russia, US, China, and EU, the inventory was very close to the total of the inversions, both GOSAT and in situ data. Now going to N2O. N2O is very difficult because we have very few stations, the fluxes are not well known, and the inventories are very difficult, in particular for indirect emissions, where national agencies apply some ad hoc factors to calculate the amount of N2O coming out from inland waters, anthropogenic effects, and also from atmospheric nitrogen deposition. So we found some large differences. Again, a tendency of inventories to underreport the total emissions, in particular for Mexico. This was very striking, but also for Australia. I got contacted after this paper by the Australian government, and they think they could have some problem with their emission factors. Also for Indonesia and also for India. But we have to say that it's very difficult because N2O, it has also some natural emissions, and it's very difficult to separate the two terms. So this is now a summary of the results, how good or how badly do the inversions compare with the inventories. This is for CO2. First of all, you have in red the fossil emissions, and I would have expected them to be the same because the inversions are using as a prior emissions which should come from inventories, but still there are differences in the way inverse modelers interpolate fossil emission fields, and these differences are reflected between the difference between the red circles and the red bars. On the other hand, for the green bars, there is, generally speaking, a relatively good agreement between the mean decadal value of the sink of carbon between inversion and inventories. I will pass on this slide. Back on methane, an important point is that a fraction of the emission occurs with leaks from maintenance or accidental events. Those leaks can be very large, and we now have the possibility to measure emissions from ultra leaks. We are talking about really big sporadic emissions on the order of 20 or more ton of methane emitted each hour. Of course, they don't last very long. And we've been using a systematic analysis made by our colleagues from Kairos. They are using the high-split transport model and the tropomy images to capture every plume. And they detected a number of events, which is shown on the upper left plot. In total, it's about 2,000 events. Most of them are coming from oil and gas leaks. A few are coming from coal mines, and another few from other human activities. And you can see the location of all those big leaks events which have been detected around the world over the last 2 years. A lot of them in Iran and Kuwait, in Algeria, also along the Russian pipelines. They are very well visible in Central Asia, and also some places of Pakistan and India and northern China in the Shaanxi Basin where coal is extracted. Those ultra leaks, we consider that they are not seen by inventories because they are not included in the emission factors which are used by national agencies. So they should be essentially added to inventories, and then we will look if adding this kind of missed ultra leak emissions will make the comparison better. The figure is showing the fraction of ultra emitters as a fraction of the total national inventory for different countries, and the situation is contrasted. For the US and for Russia, typically it's 5% of the emissions which are probably missed by the inventories because of those accidental leaks. For other countries, in particular Turkmenistan, it is as much as 100% of the national inventory which occurs as ultra leaks. And Turkmenistan is particularly strong. They have some compressors or some facilities that have very large emissions, which unfortunately are lasting for many months. So in this case, of course, the amount of ultra leaks is very important. So this is a summary of the kind of big picture for the methane. Each group of 3 bars is one country. The first 2 bars are the average of the inversion for the last 10 years for methane. The gray area is the fossil sector, and the agricultural sector is in yellow. And on the right, for each country, you have the UNFCCC inventory. We have also analyzed separately some emission basins, also using tropomy, but it's another type of inversion. It's a regional inversion for some extraction basins, like in Iran or in the Permian or the Appalachian or the Bowen Basin in Australia. But we consider that this is seen by global inversions. It's just a way to attribute the global fossil inversion of a country to some kind of hotspot regions where the gas or the oil or the coal is extracted. And then we added the ultra-emitting leaks. You can see a very long one here. I think it's from Algeria here. It's about it's a plume of about 400 kilometers long, so it's really a very big event. So the ultra emitters do increase the emissions if you add them on top of the official inventories, but not too much. And still, you have some. It makes for Turkmenistan and Kazakhstan. It makes a comparison with inversion much better. But still, we can see, you can appreciate some of the differences between reported emissions and inversions. Generally speaking, within the error bars of the two approaches, they are broadly comparable, but there are still individual countries where there is a strong underreporting, in particular in the Middle East. This is the same figure for N2O. So again, we have the three inversions, and we have the UNFCCC data, which we split into direct energy sector-related emissions and agriculture emissions. So not surprisingly, agriculture emissions are the largest in all the countries. And here you see that we have very large differences. We were very surprised to see that even when you consider only managed land in your N2O inversion analysis, for countries like India, but also Brazil, and many tropical countries, the Democratic Republic of Congo, Venezuela, Indonesia, Mexico, there was always a significant, let's say, higher estimation of the anthropogenic N2 emissions by inversions compared to national reports. And I don't know quite what is the reason for that, but it's something we need to consider and we need to work on if we want to improve the way inventories are prepared. So I will come to my conclusion. First of all, I think it was the first time that we kind of dared to compare global inversion results with national inventories. Of course, we did that only for large emitting and large area countries. We found that it is important to make the comparison fair, to sample gridded inversion fluxes for managed lands. We use different proxies for that, but this, of course, could be improved if countries could report a spatially explicit data set about their managed land areas. We found that we need to correct CO2 inversions for lateral fluxes to make them comparable with bottom-up inventories, mainly because inventories are carbon stock changes, which are different from the land atmosphere CO2 fluxes. As a result, we discovered that most northern, in particular northern boreal countries like Canada and Russia, appear to underestimate their carbon sink in the LULUCF sector. No clear explanation for that, but Canada and Russia don't have a sample-based forest inventory. They use a kind of bookkeeping model, and one possibility is that the kind of forest growth curve that they are using to establish their carbon stock change is ignoring the effect of rising CO2 and climate, longer growing season in cold regions, that could make the carbon sink higher than what is calculated by the bookkeeping model used by inventories. Regarding CH4, in particular fossil CH4 emissions, generally speaking, for all the oil and gas extracting countries, we found that fossil CH4 emissions, which are declared to the UNFCCC, are significantly less than the inversion. So there is clearly some work to do here to improve the inventory method and also to reduce the uncertainty on the spread of inversions. For agricultural methane emissions, we also found that reported emissions are lower than inversions for some countries, large agricultural countries like India, Brazil, and Indonesia. But we have to be careful, of course, because those countries also have wetlands, and the way we separate natural from anthropogenic sources has, of course, some uncertainty in the deduction of agricultural and waste methane emissions. For N2 emissions, we also found that there is a significantly lower numbers from the available inventories compared to the inversions. But again, the number of atmospheric sample data is very sparse. So it's also difficult to have, let's say, a small uncertainty on N2O budgets for anthropogenic emissions. What we are doing now is trying to exploit better satellite data for CO2 inversion. We use GOSAT and TROPOMI for methane, but we haven't used the GOSAT and OCO2 data for inversions. So we are now collecting inversion data based on OCO2, in particular with colleagues from NATA GPL, to improve the comparison. We hope that the OCO2 data will provide a better sampling over tropical countries, so it will probably give a different estimate and an interesting estimate of the carbon balance of those countries, which is very poorly constrained by in situ measurements. And also, we want to systematically complete the attribution of the global CH4 emissions using those regional high-resolution inversion estimates from ultra-emitters and emitting basins. So with that, I will stop, and I would like to thank you for your attention.
Yeah, okay. Thank you, Dr. Philip. It was really very interesting talk. And we have some questions in the chat box. So first question from Dr. Prabir Patra is asking that can there be a way to remove natural effect on CO2 fluxes estimated by inversion before comparing with the inventories? Some of the variabilities looks large, for example, for Australia.
Yeah, thank you for the question. It's a very good question. I think what we wanted to do is to compare inversion, to make them comparable with inventories, and all sample-based inventories, essentially all inventories that have successive sampling of forest plots, they include climate effects. If you have 5 years of revisit to make a forest inventory, if you have droughts or fire disturbances, normally this should be included. So there is no missing carbon. However, the devil is in the details, because you have this managed land issue, which I pointed out, and also the fact that for disturbances, countries have the choice in their report. Either they include disturbances, and then, of course, they include the regrowth carbon sink after disturbances, so they have more loss, but they enjoy more regrowth. Or they can also decide to say, okay, big fires, for instance, in Canada, they are due to nature, so we don't put them in our inventories, but if they do that, they have to be honest, and they cannot count the recovery sink. Otherwise, it would be too easy. You lose carbon and you don't count it, and then afterwards, during 30 years, you gain carbon and you count it. So they have the choice to exclude or include disturbances. And of course, when we process inversions, we don't have this choice. So if we want to answer Prabir's question, we need to look really at how different land use sector inventories are computed. I must say that these inventories sometimes are very good for biomass. For soil, they are very uncertain because nobody is measuring the carbon change in the soil carbon. It's always some models. And even countries that have a very good inventory system, for many ecosystems, they have no data. Like I found that Germany, for grassland on mineral soil, they have no soil carbon inventory. So they say it's neutral. And they say in our spreadsheet, we put 0 because we have no data. In a sense, it's honest, but of course, we don't know if managed pasture in Germany are sink or source of carbon. So we have to also account for the fact that many countries, when they have no data, they say we put 0 or we put a default value. So this is also an important source of uncertainty that needs to be considered when you compare inversions with inventories.
Yeah. Okay, thank you. And then one more question from his side. What are the differences between EDGAR and national inventory for N2O emissions from India? EDGAR emissions generally fits well with model simulation inversions.
Yes, I did not look at that, so I cannot show you the picture. I did it for methane, but not for N2O, but it's a very good suggestion. And we could indeed compare EDGAR with inversions. I have not done it, so I cannot say anything. What we tried to do is to identify indirect emissions, because we use only the UNFCCC For many countries, including India, countries report their indirect emissions, which are about 15 to 20% of the direct emissions, so they are significant. But we found that for many non-Annex 1 countries, in particular all the countries in Africa and many countries in South America, in their national communications, there is no report of indirect emissions. So, of course, if countries omit to report their indirect emissions, it could also explain why their UNFCCC estimation is less than inversions. But it's a very good idea indeed to compare with EDGAR, which has essentially all the sectors. Huh?
Yeah. And one more question from Imran. When countries report their emissions, do they report about error or the methodology adopted for their reported emission?
So I'm not an expert. I think they have to explain the method they used. They have the choice. They can use a tier 1, a tier 2, or tier 3, but they have to explain what method they choose, and in principle, what are the emission factors. And normally, they also report some uncertainty, and the uncertainty is based, at best, using some Monte Carlo analysis. They have an activity, and on the emission factors, they have a distribution, which they take as being Gaussian or log normal, and they do a random sampling of different emission factor values, for instance, for waste, methane emissions, and they derive an uncertainty from that. The difficulty is that, generally speaking, in terms of activity data, if you want a number of cows, for instance, there is no alternative data set. In the end, it's only national data. Even the FAO, their activity data is from national data. So you cannot do a Monte Carlo on activity data because in the end, at the beginning, there is only a single source. If you want to know how much coal is used by India, the countries come from the data come from the Indian government. Of course, you have CDIAC, you have BP statistics, but at the base, they all use data which are reported by the Indian government. So there is no second data set for this type of emissions. So it's difficult to estimate uncertainty from activity data, and it's possible using Monte Carlo method to estimate uncertainties from emission factors. Of course, for CO2 emission factors, not very important, but for methane and N2O, the uncertainty of emission factors is very important.
Yeah, yeah, thank you. And one more related question. What is the uncertainty of EDGAR methane inventory over India?
I don't know. I don't know if EDGAR is providing an uncertainty estimation, but it's something we could look at because the advantage of EDGAR is that there are different versions. There are version 2, 3, 4, 5, and 6. And maybe one good way to analyze the uncertainty of EDGAR is to compare the successive versions. I know that for coal in China, the EDGAR V2 had a huge emissions because they have a lot of super emitting mines, and then they reduced it in V4. So one way to assess the uncertainty of an inventory like EDGAR, if they don't do a formal uncertainty analysis, is to compare successive versions of their inventories. But I have not done it. I'm working on this for methane, but I have not done it yet.
Okay. Okay, we have time for a little more question. If anyone has any question, then you can directly ask by unmuting, or you can raise your hand. Okay, I guess all are really satisfied with the really great talk. Thank you, Philip. Yeah, so one more question from Vinu. In methane inversion, what are the appropriate values of observational uncertainty?
Yeah, so that's, of course, each inverse modeling group is using its own recipe. For in-situ data, the instrumental error is very small. It's something like 5 ppb. But modelers are accounting for the errors due to the fact that coarse scale transport models have difficulties to represent a station as a point measurement. And generally speaking, they use typically the kind of synoptic variance or misfit between model and data to increase the error to account for this representation error. The problem, as I say, is that normally all the errors in inversion are treated as random errors. So you can have a larger error to account for the misrepresentation of transport effect. But if you treat it as a random error, in the end, if you have a lot of measurements, it will not matter too much. I think we have much more problem of representation either with a systematic error. For instance, if you have a site which is in a valley and it's receiving more methane, so it's always higher than the inversion. If it's a bias, it will constrain the solution of the inversion. But if you don't know the magnitude of this bias, of course, it cannot be included easily in inversion. About the satellite products, I don't really know. I think they take, maybe Prabir knows better than I think they take the kind of reported error on the retrieval and they probably aggregate different GOSAT soundings plus some transport errors. There is also some GOSAT bias, and sometimes the GOSAT is different from the in situ. Of course, it's a colon versus point, but there are also some inversions, I think, which are applying some kind of bias correction to the GOSAT data when they assimilate them together with in situ data.
Yeah.
Probably Prabir knows more than I about this.
No, Philip, I have nothing to add. Very nice. Fantastic.
Yeah. Yeah, thank you, Philip. By the way, in chat box, Shamil has given one reference paper where Edgar uncertainties are basically published. So those who are interested may please follow that paper. Yeah.
Okay, thank you. I will look at it.
Yeah, so thank you, Philip, for a really very informative talks, and then the young scientists, then young researchers who are attending, I'm sure they have learned a lot, and then they will basically follow you in future via email and then on your website. So thank you very much for giving the talk and just coming here. Thank you. So Vinu, over to you for the next program.
Okay, thank you, Yogesh, for chairing this session. Now we have come to the end of the plenary and keynote talks of the day, and we are now splitting into two groups. One group will go to the panel discussion, and more members will be joining us for the panel discussion starting from 3:30. At the same time, the registered participants and trainees who are attending this session will have to join to the second link, which is the training link. So I request the trainees to kindly log out from here and join the second link. And panel discussion will start at 3:30. So the members will be still joining. So it will take some time for all of them to arrive. So maybe we can wait until 3:25 and come back and attend them. Thank you.
So is Philip going to stick around or leaving?
Philip is already left, I think.
Okay.
Yes. So I request all the participants who are registered participants kindly move on to the training link, the link number 2 that we have communicated. Thank you.
And if, of course, if anybody want to discuss this Philip's talk here also is very nice because that was like maybe they are like too much afraid to ask Philip any questions.
Yes, it was too big to ask to Philip.
Yes, but this is like very nice, man. Please discuss among yourself or discuss with your the other scientists here. So feel free and.
I want to say hi to Shamil. Shamil, are you able to hear us?
Hello, Shamil.
I'm here.
Yeah, Shamil.
Glad to see you.
Good evening.
Hi. I will stay. Okay.
Yeah. That's a nice reference, Shamil. That's yeah.
Yeah. Thank you, Shamil.
So today for panel discussion, I can tell the appropriate number we are expecting around. We have contacted 20 people, but I'm not sure all of them will be joining. But let's see how many are finally joining today.
So panel discussion on this link, right?
Yeah. So on this link only.
Okay.
So we have 5 minutes break.
Yeah, 5 minutes break. Yes.
Okay. So Avi will start his training in another link.
Yes, I'll just catch up on them, how they are doing.
Yeah.
Panelists, please hold on. We are all converting your status into presentees. It will take some time. Please hold on.